สวัสดีค่ะสวัสดีทุกท่านนะคะต้อนรับทุกท่านเข้าสู่เช้าวันที่2ของ Thaicid-Nwiks 2026ในวันนี้นะคะที่อาคาร80ปีมหาวิทยาลัยเกษตรศาสตร์วิทยาเขตกำแพงแสนค่ะวันนี้นะคะเป็นอีเวนท์ที่จัดขึ้นโดยดงตาลซอฟต์แวร์เดย์ค่ะภายในธีมของการปรับโครงสร้างพื้นฐานสู่ระบบชลประทานและการระบายน้ำอัจฉริยะเพื่อความยืดหยุ่นในยุคภูมิอากาศเปลี่ยนแปลงค่ะดิฉันอิงค์ ณัฐภัส วงศ์เภาค่ะรู้สึกเป็นเกียรติเป็นอย่างยิ่งเลยค่ะที่ได้รับหน้าที่เป็นพิธีกรในวันที่2วันนี้นะคะ A very good morning, ladies and gentlemen, and everyone participating in this room. Welcome to the second day of this Thaicid-Nwiks 2026. This is a warm and the fresh morning, and welcome to this 80 years building. Thaicid University, Kamphaeng San campus right here. Today's event is held by Dong Tan Software Day in the theme of adaptive infrastructures for smart irrigation and drainage systems, engineering resilience in the age of climate change. วันนี้นะคะใครที่มาเก็บตัวคะแนนของ CPD นะคะเดี๋ยวขออนุญาตแจ้งคร่าวๆให้น้องๆเข้าใจกันสักนิดหนึ่งนะคะสำหรับคะแนน CPD ค่ะน้องๆจำเป็นจะต้องสแกน QR Code ให้ครบทั้ง3จุดถึงจะได้รับการเก็บอย่างถูกต้องนะคะจุดที่1คือจุดที่ลงทะเบียนบริเวณด้านหน้านะคะอันนั้นจะเป็น1จุดที่จำเป็นจะต้องสแกนก่อนเข้าห้องเลยจุดที่2ก็คือการเช็คอินกิจกรรมที่ขึ้นตอนนี้นะคะแล้วก็จุดที่3คือเมื่อหมดเซสชันของแต่ละเซสชันจะเป็นการสแกน QR Code เพื่อเช็คเอาท์ดังนั้นนั่นแปลว่าน้องๆจะยังคงเหลืออีก4เซสชันในการเก็บ CPD นะคะก็คือเซสชันเช้าวันนี้สแกนล็อกอินตอนนี้เช็คอินตอนนี้นะคะแล้วก็เช็คเอาท์ตอน 12 นาฬิกาเซสชันที่2คือเซสชันของบ่ายวันนี้เช็คอินตอน 13 นาฬิกาและเช็คเอาท์ตอน 16 นาฬิกาและวันพรุ่งนี้อีก2เซสชันก็คือช่วงเช้าและช่วงบ่ายเช็คอินและเช็คเอาท์ในเวลาเดียวกันค่ะสำหรับหลักเกณฑ์ของการใช้คะแนน CPD นะคะก็คือต้องบอกว่า CPD เนี่ยเป็นหน่วยพัฒนาความรู้หรือระบบคะแนนที่สภาวิศวกรนะคะกำหนดขึ้นนะคะเพื่อให้วิศวกรพัฒนาตัวเองอย่างต่อเนื่องดังนั้นจะถูกนำไปใช้เป็นเกณฑ์บังคับในการยื่นเพื่อที่จะเลื่อนระดับเป็นสามัญวิศวกรและวุฒิวิศวกรรวมถึงใช้ในการต่ออายุใบอนุญาตประกอบวิชาชีพด้วยทีนี้วิธีการสะสมคะแนนค่ะทุกท่านก็สามารถที่จะสะสมคะแนนแบบนี้นะคะไปเรื่อยๆแล้วก็การที่จะขอเลื่อนระดับเนี่ยจะต้องใช้ CPD อย่างน้อย150หน่วยความรู้หรือว่า150 PTUค่ะอายุของคะแนนเมื่อเก็บแล้วนะคะเมื่อนำไปใช้สามารถที่จะต้องใช้ภายใน3ปีนะคะนั่นแปลว่าเวลาในการใช้คะแนนเนี่ยจะต้องเป็นการเก็บหน่วยที่ไม่เกิน3ปีนั่นเองอายุคะแนนค่ะแล้วก็การสะสมคะแนนนะคะสามารถสะสมได้ตามหลักเกณฑ์ดังนี้นะคะการเข้าอบรมสัมมนาการเป็นวิทยากรการเขียนบทความทางวิชาการหรือจะเป็นการทำจิตอาสาในงานวิศวกรรมก็ได้ค่ะแล้วก็วิศวกรสามารถตรวจสอบการจัดหน่วยคะแนนเองได้ที่ระบบบริการ CPD ของสภาวิศวกรนั่นเองค่ะอย่าลืมนะคะว่าต้องลงทะเบียนแล้วก็สแกน QR Code ทั้งหมด3จุดถึงจะ complete นะคะจุดลงทะเบียนเช็คอินและเช็คเอาท์ให้ถูกต้องค่ะเอาล่ะในงานวันนี้นะคะเพื่อที่จะเริ่มงานในวันนี้อย่างเป็นทางการค่ะขออนุญาตเรียนเชิญบุคคลสำคัญ1ท่านขึ้นมาพูดเปิดเวทีแล้วก็ต้อนรับทุกท่านในวันนี้อย่างอบอุ่นนะคะขออนุญาตเรียนเชิญคุณรสุสืบสหการค่ะผู้อำนวยการสถาบันพัฒนาการชลประทานขึ้นเปิดเวทีขอเสียงปรบมือด้วยค่ะ
เรียนอาจารย์สาธิต มณีผายประธานคณะทำงานด้านวิชาการไทยศิษย์อาจารย์ดร.นพดล โคสุวรรณรองประธานคณะทำงานด้านวิชาการไทยศิษย์คณะผู้บริหารผู้แทนจากกรมชลประทานมหาวิทยาลัยเกษตรศาสตร์สมาคมศิษย์เก่าวิศวกรรมชลประทานในพระบรมราชูปถัมภ์วิศวกรรมสถานแห่งประเทศไทยในพระบรมราชูปถัมภ์สภาวิศวกรสมาคมไทย IoT เครือข่ายสถาบันการศึกษาหน่วยงานภาครัฐและเอกชนท่านวิทยากรรวมทั้งผู้เข้าร่วมการประชุมทั้งในห้องประชุม และผู้รับชมผ่านระบบออนไลน์ตลอดจนพี่น้องสื่อมวลชนทุกท่านครับในนามของคณะทำงานดงตาลซอฟต์แวร์เดย์ผมมีความยินดีและรู้สึกเป็นเกียรติอย่างยิ่งครับที่ได้มาต้อนรับทุกท่านในงานดงตาลซอฟต์แวร์เดย์ประจำปี 2519 ในปีนี้ซึ่งเป็นส่วนหนึ่งของสัปดาห์เครือข่ายไทยสิทธิ์เพื่อการแลกเปลี่ยนเรียนรู้อย่างบูรณาการหรือที่เราเรียกกันว่าไทยสิทธิ์ Nwiks ในปีนี้ครับก่อนที่จะเริ่มกิจกรรมในวันนี้ครับผมอยากจะเชิญชวนทุกท่านได้ย้อนกลับไปจุดเริ่มต้นของชื่อคำว่าดงตาลซอฟต์แวร์เดย์กันเล็กน้อยครับงานดงตาลซอฟต์แวร์เดย์ในที่ผ่านมาครับเกิดขึ้นจากความตั้งใจของอดีตผู้อำนวยการสถาบันพัฒนาการชลประทานและอดีตผู้อำนวยการวิทยาลัยการชลประทานอาจารย์ชัยยะพึ่งประสบครับที่เล็งเห็นว่าการบริหารจัดการน้ำในยุคที่โลกกำลังเผชิญกับการเปลี่ยนแปลงสภาพภูมิอากาศไม่อาจใช้องค์ความรู้แบบเดิมอีกต่อไปแต่จำเป็นต้องอาศัยซอฟต์แวร์เทคโนโลยีดิจิตอล IoT AI เข้ามาช่วยเพิ่มประสิทธิภาพในการวางแผนการวิเคราะห์และการตัดสินใจครับแล้วก็แน่นอนว่าประเทศไทยเองเราก็มีนักวิจัยนักพัฒนาแล้วก็มีหน่วยงานที่มีองค์ความรู้ด้านนี้อยู่เป็นจำนวนมากครับทั้งในมหาวิทยาลัยหน่วยงานภาครัฐภาคเอกชนแล้วก็เครือข่ายความร่วมมือระหว่างประเทศด้วยถ้าหากเราสามารถรวบรวมองค์ความรู้เหล่านี้ครับมาแลกเปลี่ยนถ่ายทอดแล้วก็ต่อยอดร่วมกันเนี่ยมันก็คงจะเกิดประโยชน์ต่อการบริหารจัดการน้ำของประเทศเป็นอย่างมากครับจากความตั้งใจในวันนั้นครับจึงเกิดการประชุมครั้งนี้ขึ้นด้วยความร่วมมือระหว่างกรมชลประทานกับมหาวิทยาลัยเกษตรศาสตร์โดยคณะวิศวกรรมศาสตร์และคณะวิศวกรรมศาสตร์กำแพงแสนเกิดขึ้นครั้งแรกณวิทยาลัยการชลประทานเมื่อปี 2565 หลายท่านอาจทราบว่าวิทยาลัยการชลประทานครับหรือว่าโรงเรียนช่างชลประทานของเรานั้นนะไม่ได้เป็นเพียงสถาบันผลิตวิศวกรชลประทานเท่านั้นนะครับแต่ยังเป็นสถาบันต้นกำเนิดของคณะวิศวกรรมศาสตร์มหาวิทยาลัยเกษตรศาสตร์ในปัจจุบันซึ่งนั่นก็เป็นที่มาของคำว่าวิศวะดงตาลจนกลายเป็นสัญลักษณ์แห่งความผูกพันของนิสิตเก่าวิศวกรรมศาสตร์และวิทยาลัยการชลประทานสืบทอดกันจนมาถึงทุกวันนี้ครับเพราะฉะนั้นการประชุมในวันนี้เนี่ยจึงเกิดขึ้นแล้วก็ตั้งชื่อว่าดงตาลซอฟต์แวร์เดย์ครับและแน่นอนว่าเมื่อพูดถึงคำว่าดงตาลย่อมนึกถึงบุคคลคนหนึ่งครับหม่อมหลวงชูชาติกัมพูอดีตอธิบดีกรมชลประทานและอดีตอธิการบดีมหาวิทยาลัยเกษตรศาสตร์ซึ่งท่านได้สร้างคุณูปการในด้านการชลประทานครับท่านมีบทบาทสำคัญในด้านการชลประทานครับโดยเฉพาะเรื่องของการผลักดันให้ประเทศไทยครับเป็นหนึ่งใน11ประเทศผู้ก่อตั้งคณะกรรมาธิการด้านการชลประทานและการระบายน้ำนานาชาติหรือ ICID รวมทั้งท่านเป็นผู้ผลักดันนะครับแล้วก็ก่อตั้งคณะกรรมการด้านการชลประทานและการระบายน้ำประเทศไทยหรือไทยสิทธิ์นอกจากนั้นแล้วครับท่านยังดำรงตำแหน่งรองประธาน ICID ซึ่งนั่นทำให้ประเทศไทยครับได้รับการยอมรับบนเวทีด้านการชลประทานในระดับนานาชาติแล้วก็ในขณะเดียวกันครับหม่อมหลวงชูชาติกัมพูเองในฐานะอธิการบดีมหาวิทยาลัยเกษตรศาสตร์ในสมัยนั้นท่านยังเห็นว่าทุ่งบางเขนเริ่มจากคับแคบครับแล้วก็ไม่เพียงพอสำหรับการเรียนการสอนงานวิจัยงานแล้วก็งานพัฒนาท่านจึงเป็นผู้ริเริ่มขยายแนวคิดนะครับขยายวิทยาเขตมาที่กำแพงแสนครับพร้อมกับผลักดันการจัดหาแหล่งเงินทุนเพื่อพัฒนาพื้นที่แห่งนี้ครับซึ่งแม้ต้องเผชิญกับปัญหาอุปสรรคแล้วก็เสี่ยงคัดค้านในระยะแรกแต่ด้วยวิสัยทัศน์ของท่านครับท่านได้สร้างรากฐานมหาวิทยาลัยเกษตรศาสตร์วิทยาเขตกำแพงแสนครับซึ่งวันนี้ได้เติบโตเป็นศูนย์กลางด้านการศึกษาการวิจัยนวัตกรรมครับสร้างศาสตร์แห่งแผ่นดินที่สำคัญของประเทศในปัจจุบันด้วยเพราะฉะนั้นวันนี้ครับจึงนับเป็นโอกาสอันดีครับแล้วก็มีความหมายอย่างยิ่งที่ในปีนี้เนี่ยเครือข่ายไทยสิทธิ์แล้วก็ ICID ของเราครับได้กลับมาจัดกิจกรรมณมหาวิทยาลัยเกษตรศาสตร์วิทยาเขตกำแพงแสนซึ่งเป็นสถานที่ที่สะท้อนถึงวิสัยทัศน์ของหม่อมหลวงชูชาติกัมพูได้อย่างชัดเจนเพราะที่แห่งนี้ไม่ได้เป็นแค่สถานที่จัดประชุมครับแต่เป็นจุดที่เรื่องราวของการพัฒนาทรัพยากรน้ำการสร้างวิศวกรชลประทานและการพัฒนาการศึกษาด้านการชลประทานของประเทศไทยได้กลับมาบรรจบกันอีกครั้งหนึ่ง ตลอดระยะหลายปีที่ผ่านมาครับงานดวงตาลซอฟต์แวร์เดย์ได้มีการพัฒนาอย่างต่อเนื่องทั้งเนื้อหารูปแบบแล้วก็เครือข่ายครับสำหรับในปีนี้เรากำหนดงานขึ้นภายใต้ธีมที่ว่า Adaptive Infrastructure for Smart Irrigation and Drainage Systems Engineering Resilience in the Age of Climate Change. At this point, I would like to extend my warmest welcome and sincere appreciation to all our distinguished speakers, to Dr. Stanford Gibson from the Hydraulic Engineering Center, U.S. Army Corps of Engineers, and Mr. Mark Hegauner, Director of Delta-RES Singapore. Thank you very much for being here with us. We truly appreciate your time and your friendship, your willingness to share your valuable knowledge and your experiences. Your participation is an important part of making Dongtan Software Day a place where idea, innovation, and international collaboration come together. นอกจากนั้นแล้วครับยังต้องขอบคุณท่านวิทยากรอีก3ท่านนะครับที่มาช่วยเติมเต็มประสบการณ์การนำซอฟต์แวร์เด็ดๆมาใช้อย่างเป็นรูปธรรมครับท่านแรกต้องขอบคุณท่านรองศาสตราจารย์ดร.สุทธิศักดิ์สรลำครับภาควิชาวิศวกรรมโยธามหาวิทยาลัยเกษตรศาสตร์ท่านที่2ขอบคุณดร.ศิริลักษณ์ชุ่มชื่นครับบริษัทปัญญาคอนซัลแทนและท่านที่3ครับนายโรจนะสิริวัฒนภักดีครับหลายท่านอาจสงสัยว่าเมื่อเราได้มาเรียนรู้ซอฟต์แวร์ใหม่ๆแล้วครับจากผู้เชี่ยวชาญในวันนี้โดยเฉพาะผู้เชี่ยวชาญระดับโลกแล้วพวกเราได้นำโอกาสเหล่านี้ไปทำอะไรกันมาแล้วบ้างผมอยากเชิญชวนครับทุกท่านนะครับได้ร่วมค้นหาคำตอบไปพร้อมๆกันตลอดทั้งวันเพราะเป้าหมายของเราไม่ได้อยู่ที่การรู้จักซอฟต์แวร์เพียงอย่างเดียวครับแต่เป้าหมายของเราคือการนำองค์ความรู้เหล่านี้มาพัฒนาต่อยอดประยุกต์ใช้พร้อมรับมือกับความท้าทายในอนาคตสุดท้ายนี้ผมขอบคุณท่านวิทยากรทุกท่านหน่วยงานพันธมิตรผู้สนับสนุนผู้เข้าร่วมงานทุกท่านที่ร่วมกันทำให้งานดงตาลซอฟต์แวร์เดย์ของเราในปีนี้เติบโตขึ้นอย่างต่อเนื่องและขอให้ทุกท่านครับได้รับความรู้แรงบันดาลใจแล้วก็มิตรภาพใหม่ๆในระหว่างการประชุมในวันนี้ขอต้อนรับทุกท่านสู่งานดงตาลซอฟต์แวร์เดย์ประจำปี 2519 ขอบคุณครับ
ค่ะขอเสียงปรบมือนะคะให้กับคุณรัสูสืบสหการนะคะผู้อำนวยการสถาบันพัฒนาการชลประทานขอเรียนเชิญท่านยังคงอยู่บนเวทีกับเรานะคะและขอเรียนเชิญเพิ่มเติมเพื่อขึ้นมาถ่ายภาพความประทับใจนี้พร้อมๆกันค่ะท่านแรกค่ะคุณสาธิตมณีผายค่ะขอเรียนเชิญเลยค่ะขอเสียงปรบมือให้ท่านด้วยนะคะท่านที่2นะคะขออนุญาตเรียนเชิญคุณนพดลโคสุวรรณค่ะเรียนเชิญเลยค่ะขอเสียงปรบมือให้ท่านด้วยนะคะตามมาด้วยค่ะคุณกรตะสุวรรณโพสุวรรณค่ะเรียนเชิญเลยค่ะขอบคุณค่ะ And then may I invite Mr. Mark Hegauner on the stage for this photo session in this morning ขอเสียงปรบมือให้ท่านด้วยค่ะคุณโรจนะสิริวัฒนภักดีค่ะเรียนเชิญเลยค่ะค่ะขอบคุณค่ะและท่านสุดท้ายค่ะผู้ช่วยศาสตราจารย์ดร.ชูพันธ์ชมพูจันทร์ค่ะเรียนเชิญค่ะในวันนี้นะคะต้องบอกเลยนะคะว่าตามเจตจำนงค่ะที่ดงตาลซอฟต์แวร์นะเขาได้ก่อตั้งมาตั้งแต่แรกนะคะคือต้องการให้วิศวกรรมกับเรื่องของระบบชลประทานมาบรรจบกันแบบบูรณาการนั่นเองค่ะนำความรู้เทคโนโลยีต่างๆนะคะมาเพื่ออัดแอปใช้ในปัจจุบันนั่นเองค่ะโอเคค่ะในโอกาสนี้คิดว่าช็อตแรกเรียบร้อยแล้วเดี๋ยวสักครู่ค่ะทุกท่านยังคงอยู่บนเวทีนะคะทุกท่านเดี๋ยวรอสักครู่นะคะเพราะว่าเรายังมีอีก1ช็อตค่ะขอเรียนเชิญผู้เข้าร่วมงานจาก Zoom ขึ้นมาได้เลยค่ะ and right now we still have one more person at the Zoom online platform who is going to take a photo with us. Welcome you once again, Dr. Stanford Gibson. Yeah, so you can look right through the camera. We're going to take a photo together with the offline personnel right here on the stage. ค่ะเรียนเชิญเลยนะคะตากล้องเรียบร้อยไหมคะตากล้องโอเคขอบคุณค่ะขอบพระคุณทุกท่านนะคะ thank you everyone ขอบคุณนะคะ thank you and we're going to pass you through the next session โอกาสนี้ขอเรียนเชิญคุณชูพันธ์ชมพูจันทร์ยังคงอยู่บนเวทีกับเรานะคะเนื่องจากท่านจะทำหน้าที่เป็น moderator แล้วก็เป็นวิทยากรที่จะมานำเสนอแล้วก็เป็นผู้ดำเนินรายการต่อจากนี้นะคะ and of course Dr. Stanford Gibson you stay with us right now because you're going to be the next speakers on the next sessions that is the reservoir sediment management that's going to be held by Dr. Stanford Gibson sediment specialist at the Hydraulic Engineering Center or HEZ U.S. Army Corps of Engineersต่อไปนะคะจะเป็นช่วงเวลาที่เราจะมาพูดคุยนะคะแล้วก็เป็นเนื้อหาการบรรยายจากดร. Stanford Gibson ค่ะซึ่งจะพูดคุยในหัวข้อของการบริหารจัดการตะกอนน้ำในอ่างเก็บน้ำนั่นเองค่ะดังนั้นโอกาสนี้นะคะเดี๋ยวอิงจะขออนุญาตส่งมอบเวทีให้กับผู้ดำเนินรายการต่อไปนั่นก็คือดร. ชูพันธ์ชมพูจันทร์ค่ะขอเสียงปรบมือให้ท่านอีกครั้งหนึ่งค่ะ
ครับสวัสดีทุกท่านครับผมผู้ช่วยศาสตราจารย์ดร.ชูพันธ์ชมพูจันทร์ครับจากภาควิชาวิศวกรรมชลประทานนะครับของมหาวิทยาลัยเกษตรศาสตร์วิทยาเขตกำแพงแสนนะครับก็ขอบคุณนะครับทางกรมชลประทานและผู้จัดนะครับงานไทยศิษย์ที่ให้ผมมาเป็นโมเดเลเตอร์ในวันนี้นะครับก็ยินดีเป็นอย่างยิ่งนะครับก็วันนี้นะครับเราก็ได้รับเกียรตินะครับจากของทางดร. Stanford Gibson นะครับของทางเฮกนะครับHydraulic Engineer Center นะครับที่จะมาบรรยายกับพวกเราในวันนี้นะครับเดี๋ยวขออนุญาตนั่งนะครับโอเค Good morning Mr. Gibson on behalf of participants from Thailand including officer from the Royal Irrigation Department several lecturers, students, and water resources professionals. I would like to welcome you to today's session. Can you hear me clearly? Dr. Gibson, can you hear me?
Yes, I can.
Okay. We can see you now on the screen. Okay. Many participants today have used some of us have used HEC-LAS for hydraulic or flood modeling. But your presentation today is related to the sediment modeling. Maybe it's new for many of us. We look forward to learn about sediment load estimation, reservoir deposition, flushing, and HEC-LAS application. If everything is ready, please go start for your presentation. Maybe you can start present for around 1 hour. And after your presentation, I will briefly summarize the key points in Thai. And then we will open the floor for the question. Dr. Gibson, the floor is yours.
Great, thank you very much. Would you like me to go to 10:15 or to 10? Right, I will go. Hello, my name is Stanford Gibson, and I'm going to talk today about reservoir sediment modeling. As the introduction said, many of you have used HEC-RAS, but one of the things that we use it a lot for with respect to infrastructure sustainability is our reservoirs. This is some work that we've done in Thailand as well. And so that's going to be our topic today. Before I start, I would like to talk a little bit about what is called the Google Ngram. It turns out that before Google has all the books. They have, many years ago, they started scanning all the books. And before they fed all those books to an AI to create their LLMs, you used to be able to plot trends in, things that happened in the English language over the course of 200 years. And these could often be quite interesting. A fun example is take two kind of mythical monsters from, American movies, zombies and vampires. And if you put them into the Google Ngram, you get a time series of the percentage of all published words for each year that is represented by each of these creatures. And so you learn a couple of things very quickly that I didn't know about these creatures. One is that vampires are a very old creature. They've been around since the 1800s. They were most popular in the 1850s, whereas zombies are a modern creature. The whole zombie myth came out of the technological fear that came out of the world wars. And so you can learn things about cultural trends from the Google Ngram. Okay, let's use a couple more salient words, a couple of words that maybe we work with professionally. Dam and sediment. If I put the word dam into the Google Ngram, you see something that looks kind of like a hydrograph. The word dam peaked in about 1910, 1920, when the Western world was, when North America and Europe were building most of their dams. It kind of looks like a hydrograph. And then if you put in the word sediment, you'll see that actually that is offset by about 80 years. It's almost like a lagged hydrograph. And the moral of this story is that if you build dams, you will eventually have to deal with sediment. My friend John Shelley likes to say that all reservoirs have a 100% sediment filling failure mode. It's just a matter of how long. And so in the US, a lot of our dams are getting to be 80, 100, 120 years old, well past their design life, but we still need them. And so reservoir sediment management is something that's very important, and we use RAS in order to do those kinds of analyses. And so I'm going to talk to you about three things. We're going to talk about estimating the sediment load. We have some data analysis tools in RAS, and one of the reasons that this is so important is that when you start working with models, you start to learn very quickly that models are only as good as the data that you put in them. And sediment data are very noisy. And so we've actually developed some tools to help people make the best trends out of their sediment data for the boundary conditions of their model. That's actually the first part. I actually spend quite a bit of time on my sediment model before I even open the hydraulic model, because I want to make sure I understand the data and I'm building good boundary conditions. And then we're going to talk about using a sediment model to simulate deposition in a reservoir, to do a kind of life cycle analysis to see how long we have before sediment impacts various parts of our reservoir. And then when we're talking about sustainability, one of the things we talk about is how to manage sediment in our reservoirs so that we can extend the life. And one of the ways we do that is with reservoir flushing. And so I'm going to tell you a couple of stories about how we're flushing some of our reservoirs in the United States and how we're using models in order to simulate that. Okay, so part one, let's talk about estimating our sediment loads. And so this is a very classic sediment data plot. Usually we plot the flow or the discharge against the sediment load or concentration. The reason we do that is because we very rarely have daily sediment data that we could put into a boundary condition. And so usually what we have are daily flows or hourly flows that we can use as an upstream boundary condition. And for each of those flows, we're going to choose a load off of this relationship. But you already see the problem. When we talk about these sediment load rating curves, we often call them the data cloud, because there's over an order of magnitude of scour around a central trend. Here I've actually plotted some of the distributions of the local cloud, and so you can kind of see the way that they vary. It's very difficult to choose a single relationship in order to represent this cloud. And so what I've found is over the years, people have done very different things. They've gotten very different answers in order to try to simulate this. And so we've developed some tools right in RAS to help people interact with their sediment data. And so I'm actually going to stop presenting right now, and I'm going to bring up RAS. And you don't actually even need a RAS model. I have RAS open, but I don't have a project or a model in there. I'm going to go to what's called the hydraulic design function. And the hydraulic design is a set of it's a toolbox with simplified sediment analyses that can help you get to sediment answers very quickly. And if I go down to the rating curve calculator, we have this tool that helps you build sediment rating curves. Now in the US, you can push this button and go directly to a gauge and download the data, but that's not very helpful to you. So the other thing we've done is we've allowed you to import comma delimited data. And so we have developed the data from, and the Thailand models that I'm going to show you are all from Lam Prong Plong. I apologize for my pronunciation. Around here we call it LPP to help us with that. But I've put them in comma delimited format. And so I can just import them into the tool. And now you have all of your flow and load data, and you have the best linear regression through them with what we call a bias correction that corrects for some log bias. But in many cases, a single line does a poor job of generating this relationship. So we've also added what we call a piecewise linear tool that allows you to fit two continuous curves to your data. And so if we come in here and say, I want to have a piecewise linear regression of the upper half, what you can see is that now we fit two curves, one through the low flow data and one through the high flow data. And you might think, well, that's not a lot of points up there to get their own regression, but this inflection point is often at bank full flow, and sediment transport is nonlinear. This is log space. So at these flows, these loads almost don't matter for sediment management. These are loads of 1 ton per day or 10 tons per day. Bankful flow is 10,000, and you can get up to 50,000. These matter much more. So it's very important to get your regression correct through these upper loads. And that's why we allow you to do this piecewise linear relationship to figure out what your flow load relationship is. And then if you want to do something a little more sophisticated, we allow you to do a low S analysis. That is a local regression. What a local regression is it essentially just looks at the regression for various chunks of your data. It's a moving window regression. And so you can see that down here, you're actually inflected up, but that doesn't matter because those loads are so small that they're not going to affect your reservoir. But you can see that our local regression also shows that you have this inflection point and your higher loads are lower relative to your flows, which is going to matter a lot for what you compute as your annual flux into your reservoir. And so since we've built this tool, I've looked at a lot of inflected piecewise linear rating curves. And what I've found is that in the US, many of them are concave. The higher loads have a lower slope than the lower loads, or convex. The higher loads have a higher slope than the lower ones. And so I guess if I was there with you and we were just teaching, I would ask you all to develop a hypothesis. Which of these do you think is most common? Now, I can't see you, but I want you to imagine in your mind, which of these do you think is more common? Concave or convex? Well, I can tell you, I thought it was concave because this is what we call a supply limited situation. Supply limitation is a case where as flow increases, you kind of run out of sediment. And so instead of having this line continue to be directly related, you end up with this kind of leaned over or lower loads at the higher flows. And the implication for sediment management is that if you were to use just a linear model here, you would tend to overpredict your load. And if you use the linear model here, you would tend to underpredict your load. Well, we looked at 1,300 gauges across the United States. And if you chose this one, or if you chose this one as the dominant shape, you were pretty much right, because it was about 50-50 in the United States. And so we're really interested in when would they be concave and when would they be convex. And so we mapped them in the United States. What you'll notice is the blue are our concave curves and the red are our convex curves. The concave curves tend to cluster in the central United States, while the convex curves tend to be in the coasts, the Rocky Mountains, and the desert Southwest. Now, if you're not familiar with the United States geography, which of course there's no reason you should be unless you've been following the World Cup and Kansas City is in the blue, we have all of our big sandbed rivers are in the center of our country, whereas a lot of our smaller gravel bed steep rivers are in the coasts and the Rockies. In gravel bed rivers, you have low transport until you hit a threshold that transports the gravel, and then things increase quickly. Whereas in sandbed rivers, you increase until you essentially run out of sediment, especially in rivers with reservoirs that are supply limited, and then your rating curve leans over. And so understanding how your rating curve relationships can change with respect to your watershed can help you determine the boundary conditions for your model. Because the boundary conditions for your model are maybe the most important part. But once you understand your data, now you want to model deposition. And I think one of the questions you might ask, or that your manager might ask, is that why would you model deposition? If we can use a rating curve to compute an annual load, well, isn't that math very simple? How long will it take for our reservoir to fill up? Well, we have our annual load. We multiply that times years. That's going to be the volume of the reservoir that fills up. You just subtract from your volume, and that's a very simple equation. Well, there are three reasons you would actually want to build a model to simulate sediment deposition in your reservoir. The first question is, what gets trapped? And there's actually kind of two sub-questions there. One is just how much of the total sediment gets trapped. Very few reservoirs trap all the sediment. We call this the trapping efficiency. What percent of sediment that goes into the reservoir stays in the reservoir? Now, very big reservoirs can have trap efficiencies of 97, 98%, but small reservoirs, especially if there's a lot of fine material, can have trap efficiencies of 30%. And so the flux into your reservoir isn't really what matters. What matters is what's going to stay in your reservoir. And the second question about what gets trapped is, well, what kind of sediment gets trapped? Is it coarse sediment or is it fine sediment? Also, how does your trap efficiency change over time? As your reservoir deposits, there's less water and there's less residence time, so your trap efficiency actually goes down over time. You can't just multiply this because because your reservoir gets less efficient over time. And then the third question is, where does each grain class deposit? These are some classic reservoir deposition profiles from Morris and Fan. And you can have a delta where most of your sediment deposits in the upstream portion of your reservoir, or you could have this kind of bathtub effect where basically your reservoir fills from the bottom up. Well, this will have different infrastructure effects. The delta will actually cause flooding upstream because as the delta forms, it'll push up the water surface. And we've had communities that have had to be moved in the United States because the groundwater was flooding basements, or we've had to raise levees because this water surface has increased because of the delta. This has more of an effect on the outlet or the hydroelectric production. If you get sediment right up against your structure, it can affect those functions. And so where your sediment deposits and where different kinds of sediment deposit ends up mattering, and that something you can only really get with a model. So these are two sediment impacted reservoirs in the United States. This is the Tuttle Creek Reservoir. And you can see that this has this this is the bed and then the top of the sediment deposit. And you see this has this kind of nice tapering profile where Cochiti has a very distinct delta. Now, both of these reservoirs are about 30 to 40% full of sediment. In both cases, it's a big problem. But they have very different shapes because the sediment deposits have very different shapes because this tapering is almost all silt, whereas Cochiti is more sand and gravel. And so again, these come from Morris and Fan. If you're interested in reservoir sediment management, the text out there is Morris and Fan, and Greg Morris makes the PDF publicly available. If you go and Google Reservoir Sedimentation Handbook, he will mail you the PDF. It's a wonderful resource. But basically, the more silt and clay you have, the more you move away from the delta, or the more sand and gravel you have, the more you move to the delta. But then it also is a matter of how does that fall velocity relate to the total size of the reservoir? And for that, you need a model. One of the things I think is pretty interesting as people get into sediment is it's very hard to conceptualize the difference between these different things we call sediment. One of the things I've enjoyed saying recently is that sediment is actually not a very useful word because it means too many things. So if you were to take a sand particle, actual size right there, about 0.5 millimeter, and if you were to blow that sand particle up to the size of a basketball or a football, an actual football, not an American football, then if you were to scale the other grain sizes accordingly, a grain of silt would be about the size of a marble. And a clay particle would be the thickness of 2 pieces of paper. These are very different materials. They behave very differently, and they also interact in very interesting ways. And those interactions and diverse behaviors are things that a model can help you get to. And so different sediment will deposit in different areas. And so this is a classic sediment profile in a reservoir from Cantelli 2004. And this is actually very well drawn. Let me show you one that is poorly drawn. You will often see a sediment delta drawn like this. And why is this wrong? Well, if you take the pool elevation, most people think that sediment deposit ends essentially where the pool ends. But that's not how sediment works at all. The delta moves downstream, but the delta also moves upstream. And so the sediment deposits actually can deposit well above your pool elevation. This is also another way that a model can work for you. And so this is one of the most famous reservoirs in the United States. This reservoir actually didn't accidentally fill with sediment. It was the intent. After the eruption of Mount St. Helens put 4 billion tons of sediment into the watershed. And we have levees that protect communities downstream. So we couldn't accept 4 billion tons of sediment into that river. And so the Corps of Engineers built the sediment retention structure with the intent that it would fill with sediment. And so my mentor, Tony Thomas, back in 1987, he was the Corps' first sediment modeler and maybe one of the first sediment modelers in the world. He simulated what was going to happen. And so in 1999, this is actually the pool elevation, the SRS filled with sediment. You can see that this is what was measured in 1999, and this is what he projected in 1987. This was an amazing sediment model for that day. But one of the things that he would always point out to me is that most of this deposition happens above the pool elevation. And so you have to actually account for that, not just for the volume of deposition, but also if there are communities up here, that's going to fill the channel and those communities are going to get flooded. Okay, another question. I like to do my talks interactively, which doesn't really work on Zoom. So I want you to just think about the answer. If you were going to model sediment deposition and you were going to put sediment on a cross section in a reservoir, would you fill the channel or would you smoothly distribute the sediment over the profile? I'll give you a couple minutes, a couple seconds to think about that. I won't make you vote because that's embarrassing. But again, it kind of doesn't matter which one you chose, you're correct. Upstream in the reservoir, you're going to get bed load, you're going to get your sands and gravels, and they're going to fill the channel first. But downstream in your reservoir, the fine sediment is going to rain from the reservoir down and basically evenly distribute across. And so, you know, when you look at sediment deposited in a reservoir, upstream, you fill the channel first and then the overbanks. But downstream, we call it a veneer. You deposit a veneer of sediment across your reservoir. And so this is how we model sediment in RAS in one dimension. Basically, we do hydraulics just the way you would do one-dimensional steady flow in RAS, but then we use those hydraulics to compute the sediment flux. And if we have a sediment surplus or a sediment deficit, we'll change the cross-section. This here is called the Exner equation. It's fancier than it needs to be. Those differentials are just, you know, distracting. All this equation is the continuity equation. Sediment that comes in, you compare the sediment that comes in and the sediment that goes out. And if there's a difference, you either have to deposit it or erode it. And the way we do that is we change the cross-section. And so by changing these cross-sections, we can track the progression of a delta in a reservoir. And it turns out that one-dimensional modeling is often sufficient for reservoir sediment modeling. But you can also do 2D sediment modeling in HEC RAS. We have the ability to do that. And one of the nice things about 2D sediment modeling in RAS is that not only do you have more lateral resolution if you're trying to model a floodplain or a complex flow system, but also we use better equations. We use the advection diffusion equation and better bed sorting algorithms. And so often what I'll do is, even if I want to do a low resolution model, I will simulate it based on, I will build a very simplified 2D mesh and then do my sediment modeling in 2D. One of the things that is worth noting is that we have actually completely rewritten RAS, and we're calling the rewrite RAS 2025, and it is out on the street. Beta version is available. We will have our first full release very soon. We're in a kind of transition period where many people are using RAS 2025 instead of the RAS 7.0, but RAS 2025 doesn't have sediment transport yet. And so what we're actually doing in the sediment world is we're building our meshes in RAS 2025 and then bringing them over into RAS 7 in order to do our sediment modeling. We expect to have some simplified sediment modeling in RAS 2025 in the next year or so, but the full kind of 2D advection diffusion mobile bed modeling will probably be several years out. So you'll still have to be in version 7 for a while. We are posting a full RAS 2025 class with videos. And so if you want to try out RAS 2025, I recommend it. Most people who try RAS 2025 don't want to go back. It is better in many, many ways. It just doesn't have all the features yet. So when you need the features that are only in 7.0, you have to go backwards for a while. And so to build a sediment transport model, and I'm talking about doing this in HEC RAS. Many hydraulic models also do sediment transport, and most of them are excellent. You're going to hear from Deltaris after this. They make excellent software. I usually don't care what software people use. For me, I'm much more interested in the skill of the modeler than the model they're using. I think that the skill of the modeler and the comfort of the modeler with a model is much more important to me. I would rather that someone who is good at, say, Delft 3D use Delft 3D if that's what they're comfortable with, because most of the models do the physics really well. It is the skill of modeling that is usually the limiting factor. And so if you're going to build a 1D model in HC RAS, well, you need cross sections. And if these cross sections look wiggly to you, well, cross sections are wiggly. Cross sections aren't straight. They have to follow the flow path. They have to be orthogonal with flow. And the most important part of a sediment transport model is actually your hydraulic model. You have to make sure that you have a very strong hydraulic model, because sediment transport will just amplify errors in your hydraulic model. So our first rule of sediment transport modeling is to build the very best hydraulic model that you can. And so to build a sediment transport model, you need a geometry that's either cross sections or a terrain and mesh in 2D. You need flow, and then you need sediment data. And the way you get your sediment data is usually, and this is why we talked about rating curves, is you take these flows and you pick off your sediment loads or fluxes from your rating curve. And then you have to break it down by grain size. And so here we are back with our sediment transport model at Lamprang. And this is such an interesting shaped reservoir because it's wide at the upstream end. And we have some samples, some sediment samples that were taken at the edges of the reservoir that are mostly clay and silt. And so we have some bed material that we can put in. And then we need to put in our upstream flux, which comes from our rating curve. And we would want to break that down into sediment grain classes. But this is really one of the most interesting reservoirs that I've worked on. Because it has this strange kind of upside down hammer or upside down hatchet shape, the reservoir delta actually doesn't fill all of that. This is the reservoir delta right here. And so while these samples were all silt and clay, this is your sand wedge right here. Your delta actually occupies the middle of your reservoir, and then all of this material out here is clay that is diffused. And so this is actually one of the cases where a one-dimensional model doesn't actually do the job. And so we built a two-dimensional model so that we could track the progression of the sand wave down the center of this reservoir, and then the deposition of silt and clay by advection and diffusion out to the wings of the reservoir. And so just to kind of give you an example, I guess I'm gonna wrap up here with a few stories. A couple years ago, I actually took a little audit of all of the models that I've built. Here is Lamprang here, and these are all of the models that I've been involved in. These are all the models I've been involved in Planet Earth. It turns out there's a couple of other models. If you go to the example data sets in HEC RAS, you'll notice that I have modeled a couple of the sediment data sets off of rivers in Lord of the Rings in Middle Earth. But one of the models that I worked on was Arghandab Reservoir in Afghanistan. And Arghandab Reservoir, this is the watershed for Arghandab. When I first started this model, I thought that the sediment loads were really high. I thought they were high. I thought they were actually errors because they were so high. But when you look at this reservoir, it is, or if you look at this watershed, really isn't a tree in the whole thing. And so the reservoir has filled about 40% with sediment. And downstream, in the riparian zone is all subsistence farming, people who live day to day based on the water that is provided by this reservoir. If this reservoir fails to provide water, it will be a catastrophe. There'll be human life loss. And as the reservoir fills with sediment, it becomes less resilient against multi-year droughts. And so we were looking at managing the sediment here, and we had original cross sections. And we had cross sections after a couple of decades of deposition. And so here we have good calibration data because you can compute this area, multiply it by the length, and you have a volume of deposited sediment. And you can see that we were able to track the delta formation, but the question is that right? Sure, any model could do that, but did we do okay? Did we parameterize it well? And so here is a plot of the modeled sediment transport, the modeled volume change at each of those cross sections, and the measured. And you can see in a very simple model, this is a very simple model. This takes about 8 minutes to run. We're able to simulate the sediment deposition pretty well, and then could look at alternatives from there. All right, but usually your boss doesn't just want to know how bad is it. Your boss doesn't just want to know, how many years do we have until something bad happens. They want to know, what can we do about it? And so, my colleagues, Paul Boyd and Jake Helminiak, are on their way to Thailand right now. They're going to be teaching a class on reservoir sediment management. They're two of the best we have. They're close friends of mine, but also just excellent engineers. Paul was here with me in Ecuador this week and is driving to the airport to fly home for 12 hours before he joins you. They're going to talk about a wide range of reservoir sediment management technologies. I'm going to talk about just one of those technologies, and it's called flushing. Flushing is when you just open up the reservoir and flush sediment out. And it turns out that a lot of the other technologies, you can actually, do pretty good analysis without a model to get a basic idea of how much value that management is going to offer you. But with reservoir flushing, a model really helps. Now, there are two kinds of flushing. There's what we call partial or pressure flushing, and then there is drawdown or complete flushing. And a lot of people, when they think I'm going to flush my reservoir, they think, oh, I'll just open the gates and draw my reservoir down a little bit and blow the sediment out. And that just doesn't work, because you're going to erode the sediment in the upstream part of your reservoir, but it's going to deposit in your remaining pool. The only thing you really do is clean out this little area right next to your gates. The only way to really get sediment management from a flush is to do a complete drawdown, is to go to run a river for a significant amount of time, which is why anyone who is building dams now, the only responsible way to build a dam in our generation is to build it with robust low-level outlets so that generations later we can do this. We are stuck with many dams that don't have these. Any new dam should be built with this in mind. And so we've done a couple of these. I have just a couple minutes here, so I'll just tell you one of these stories and then wrap up. What the question we had is, does a 1D model do this? Can you actually simulate flushing with the 1D model? It turns out the answer is yes. We've done it with several of these, but this is Spencer Dam. Let me tell you the story of Spencer Dam, and then I'll wrap up. Spencer Dam was built in 1925. It had 10,400 acre-feet of storage, but Spencer Dam drains what we call the sandhills of Nebraska. And if your reservoir is downstream of the sandhills of Nebraska, that probably wasn't very well placed. It was completely full of sediment by 1949. And so in the 50s, they retrofitted flushing gates. And every 2 years since then, they would open the gates and flush for 2 weeks. And we found an old sardine box of photos they took every year, and had this every year they did this. And so Paul Boyd and I, we decided to treat this as an experiment. And we went out, and this is a time lapse of the drawdown. We're looking upstream into the reservoir, and you're gonna see that they're gonna open the gates right about now. And they're gonna push ahead. It pushes a head cut upstream. And one of the things that happens is that several channels form, and they kind of race each other. You have to be pretty nerdy to enjoy this race, but I am. And so these three channels, they're racing each other to see which one is gonna kind of get deeper first and capture the flow. And so these are all kind of, you see we got a lot of bank failure here. And we have a channel to the right, we have a channel to the left, and we have a channel down the middle. You're going to get a Nebraska sunrise and sunset. This channel is actually going to pinch off here, and it's going to shorten itself. It's going to capture. And so this channel is actually, the water is flowing much faster, but this part of the reservoir also has more clay. And so once the sun rises and sun sets, the winner is going to be this channel over here on the left. And so here we are in the morning. This has been left high and dry. We're going to see a couple of scientists of questionable wisdom coming over here on this sand flat to take some measurements. But that is the first day. The flush continued for several days. And the question is, can we model it? And so we developed a 1D model of this. And the U.S. Geological, we have a structure here. And then the U.S. Geological Survey took measurements of the concentration at the bridge. We also needed sediment data. And so we ended up taking bed samples in the reservoir. And even in this reservoir that was basically full of sand, you see that as we go from upstream to downstream, the material does get finer. And this is Dr. Paul Boyd collecting sediment samples. We didn't need a boat for this. This is how full of sediment this reservoir is. We just walked out there and took shovel samples. And so the first thing we did is see if we could simulate the depositional volume. And so this is the depositional model. And then we tried to model the flush. And so the USGS collected concentrations at this bridge. And these are their concentrations with our computed concentrations. And you can see that we're hitting concentrations of about 30,000 to 50,000 milligrams per liter, that's a lot of sediment, but it actually is only 3 to 5% concentration by volume. So these are barely hyperconcentrated flows. They're still Newtonian in their physics. But then what we did is we said, well, what if these concentrations are too high? The main reason that people won't let us flush reservoirs is that these concentrations downstream are too high they will contaminate water intakes, or they'll be too high for our fish communities downstream. And so we added a tool to what we call the operational rules in RAS. Operational rules, I like to say, are the feature in RAS that have the most power that the fewest people use. You can actually write code to operate your reservoir based on any hydraulic parameters in RAS. And so what we did is we just added some sediment parameters. And so with this very simple algorithm, it says, hey, if the concentration is higher than 30,000 milligrams per liter, open the gates. We get this sedograph that now spreads out the sediment signal downstream and shows us what kind of gate operations could give us this kind of compliant sediment flush. Okay, I guess one quick story to wrap it up. In your part of the world, we did build a 1D sediment model of Zaiburi Dam on the Mekong River. And Zaiburi is a dam, and so it has a low trap efficiency. Its trap efficiency is closer to 20 to 30%, but it still it still affects the operation of the structure. And what you can see also is this is the mass of the different grain classes. And so the S's are sands. The sands deposit up here. Very fine sand deposits here. Almost all of the silt and clay just moves through the system. And what we were able to show is that if you were to flush Zaiburi Dam for 1 week a year, you would regain over the life of the reservoir about half of its total operational volume. You would reduce the deposition by 50%. Okay, if you're interested in this, I have a series on YouTube on reservoir sediment modeling. And one of the cool things of the series is that the culminating video, part 3 in that series, I show how to build a 1D sediment model, and I use the LPP reservoir to do it. So I actually use a reservoir from your country to show how to build that reservoir model in RAS. I also have a sediment transport podcast, which is a very silly sentence to say out loud. But it is the whole idea behind this podcast is to take people who have good water resources backgrounds and help bring them up to speed on sediment transport. It's like I try to think of it as an accessible graduate seminar in sediment transport and fluvial geomorphology for anyone who has other backgrounds. And I do have a 4-episode mini series on reservoir sedimentation. That's season 2 that includes interviews with some of the top folks that do this kind of work. And I will pause there for recap and questions.
Okay. Thank you, Dr. Gibson, for your valuable presentation. I like you start the Google Ngram to show us that the sediment is the highlight keyword in the past 30 years, and also thank you for the YouTube episode series. But I'm looking for the episode mini series about the Lord of the Ring that I want you to see the sediment simulation for Rohan and Gondor land in the future. Okay. Before we move to the question, I would like to briefly summarize the key point in Thai for the audience for 5 minutes. Okay. โอเคครับก็เดี๋ยวก่อนจะถามตอบกันเนาะก็เดี๋ยวขอสรุปภาพรวมสั้นๆแล้วกันนะครับสำหรับผู้ฟังนะครับแต่ทีนี้ก็อาจจะมีน้องๆนิสิตหลายคนนะครับที่อยู่ในห้องนี้เนาะที่อาจจะสนใจนะครับในอนาคตเรื่องของงานเกี่ยวกับทางด้าน reservoir sediment เรื่องของการตกตะกอนในอ่างเก็บน้ำนะครับก็เราจะเห็นนะครับว่าวันนี้นะครับที่ทางดร. กิฟสันนำเสนอเนี่ยคืออาจจะไม่ใช่แค่เรื่องของการรันโปรแกรมตัวให้ glass อย่างเดียวเนาะแต่ก็จะเป็นการตอบคำถามในเชิงของการจัดการเรื่องตะกอนในอ่างเก็บน้ำว่าตะกอนมันจะเข้าอ่างยังไงตะกอนชนิดไหนที่มันจะถูกกักเก็บไว้นะครับแล้วก็ตะกอนแต่ละขนาดมันสะสมตัวที่ตำแหน่งอะไรยังไงบ้างแล้วก็ระยะยาวเนี่ยมันจะส่งผลกระทบต่อความจุของอ่างอย่างไรนะครับก็ส่วนของตัวที่เป็นเรื่องของการประเมินตัว sediment load เนี่ยนะครับก็จะเห็นว่าดร. กิฟสันโชว์ขึ้นมาว่าตัวอัตราการไหลกับปริมาณตะกอนเนี่ยก็คือมันจะมีคีย์เวิร์ดเขาเรียกว่าอะไรนะ sediment rating curve นะครับตัวนั้นก็จะเป็นตัวตั้งต้นที่สำคัญเลยนะครับ sediment rating curve ตัวนี้นะครับเพราะว่าที่เราเห็นตัวกราฟที่เขาโชว์ครับว่าถ้าในแบบจำลองทั่วไปมันจะเป็นเหมือนเป็น linear relation เป็นกราฟเส้นตรงนะครับแต่จริงๆนะครับตัวกราฟเนี่ยนะครับมันมีทั้ง2ส่วนเนาะเมื่อกี้ที่เขาโชว์นะครับเป็นแบบหัก2เส้นนะครับเป็นแบบ piecewise คือแบบเป็นกราฟแบบหักนะครับก็คือแบบ concave กับแบบ convex นะครับซึ่งที่อเมริกาเองเนี่ยมันมีทั้ง2แนวทางทั้ง2แบบเลยนะครับเพราะนั้นเนี่ยส่วนที่เป็นตัวกราฟ sediment rating curve น่าจะเป็นจุดตั้งต้นที่สำคัญนะครับในการที่จะประเมินตัวตะกอนที่สะสมหรือเคลื่อนที่ที่อยู่ในอ่างเก็บน้ำนะครับทีนี้เนี่ยตัวที่จำลองนะครับตัว deposition หรือตัวที่ตะกอนให้มันตกตะกอนเนี่ยนะครับก็เราคงจะเห็นละว่าอย่างที่ผ่านมาถ้าเราใช้ simple equation สมการง่ายๆเนาะจำนวนตะกอนที่ประมาณนะครับคูณกับจำนวนปีเป็นจำนวนตะกอนคูณปีอันนั้นคือวิธีการอย่างง่ายที่เวลาเราออกแบบโครงการเราจะนิยมใช้กันหรือแม้กระทั่งปัจจุบันที่ใช้กันอยู่ก็ยังอาจจะเป็นสมการอย่างนั้นอยู่นะครับแต่ว่าวันนี้เราจะเห็นว่าที่ดร. กิฟสันนำเสนอนะครับเขาไปไกลกว่าเรื่องของการใช้สมการแบบ simple เนาะเพราะว่าตัวสมการเนี่ยนะครับตัวแบบจำลองเนี่ยมันจำลองก็คือตัวที่เป็น sediment trap efficiency ตัวนั้นเนี่ยแล้วก็จำลองไปถึงว่าตัวตะกอนเนี่ยนะครับมันตกตะกอนแล้วมันจะเป็นรูปร่างอะไรใช่ไหมครับนะบางอันมันตกตะกอนขึ้นไปข้างบนเหนือน้ำเป็นรูปเดลต้าบางอันก็อาจจะเป็นรูปลิ่มบางอันก็อาจจะมาตกเป็นยูนิฟอร์มหรือตกที่ตัวที่เป็นอะไรนะตัวดักตะกอนของอ่างเก็บน้ำอะไรอย่างเงี้ยซึ่งพวกเนี้ยมันขึ้นอยู่กับปัจจัยหลายอย่างอันนี้ก็เพิ่งรู้เหมือนกันว่าจริงๆถ้าเป็นลักษณะของตัวเกรนไซส์ว่าถ้าเป็นแซนหรือเป็นประเภทที่เป็นอนุภาคดินทรายเนี่ยมันตกตะกอนแบบเดลต้าอยู่ข้างบนถ้าเป็นแบบเคลก็จะค่อนมาข้างล่างนิดหนึ่งอะไรอย่างเงี้ยนะครับซึ่งตรงนี้เข้าใจว่าน่าจะส่งผลต่อเรื่องของการบริหารจัดการตะกอนในอนาคตด้วยนะครับส่วนตัวที่แบบจำลองที่ดร. กิฟสันนำเสนอเนี่ยนะครับเราก็จะเห็นว่าตัวการเซตอัพแบบจำลองนะครับโดยเฉพาะส่วนที่เป็น โดเมนนะครับที่เป็นรูปทรง geometry domain ตรงบริเวณเหนือน้ำเนี่ยอันนั้นสำคัญนะครับเพราะว่าถ้าเกิดเราจำลองตัวโดเมนเหนือน้ำเนี่ยสั้นเกินไปหรือไม่เหมาะสมเนี่ยเวลาเราจำลองตัว delta formation นะครับที่มันตกเหนืออ่างเนี่ยนะครับมันอาจจะไม่สามารถจับตรงนั้นได้ดีนะครับเพราะนั้นก็ตัวงานจริงๆตัวงานสำรวจนะครับสำรวจ cross section นะครับก็น่าจะสำคัญเหมือนกันเพราะว่าถ้าเราสำรวจ cross section ได้ดีเนาะมันก็จะทำให้เราประเมินตัวตะกอนได้ดีก็ต้องดูว่าถ้าอนาคตถ้าจะทางกรมเนาะถ้าจะเอาไปใช้ต่อตรงนี้เรื่องการสำรวจ cross section แล้วก็ขอบเขตของแบบจำลองเนี่ยก็อาจจะต้องขอบเขตเหนือน้ำเนี่ยน่าจะต้องสูงขึ้นไปเพียงพอที่จะสามารถจำลองพื้นที่ตะกอนสะสมเหนืออ่างเก็บน้ำได้นะครับมีเรื่องของ one dimension กับ two dimension ของแบบจำลองนะครับคือหลายคนที่เคยเรียนอย่างน้องๆปกติอาจจะเรียน Head Class ในวิชา Computer Application อันนั้นเป็นอย่างง่ายเนาะเป็นแบบ one dimension นะครับแต่ว่าถ้าเป็นตะกอนนะครับมันมีเรื่องของทั้งเรื่องของการเคลื่อนที่แล้วจะมีเรื่องของการแผ่ด้านข้างด้วยนะครับท่านั้นถ้าเกิดตะกอนมันเคลื่อนที่ one dimension มันคือเคลื่อนที่ทิศทางเดียวแต่ถ้าเป็นการแผ่ออกมาดูว่าการที่ตะกอนมันแผ่กระจายออกไปด้านข้างเนี่ยเป็นยังไงอันนั้นอาจจะต้องเป็น two dimension นะครับแล้วก็สุดท้ายที่เป็นประเด็นเรื่องของการ flushing นะครับที่เปิดประตูตัวอ่างเก็บน้ำเนาะแล้วก็ flush ตัวตะกอนออกมานะครับอันนี้ก็คงต้องพิจารณาทั้งในเชิงของตัวไฮดรอลิกนะครับเชิงของความเข้มข้นของตัวตะกอนด้วยนะครับเพราะว่ามันจะflushing ออกมาแล้วมันก็จะเกิดผลกระทบต่อบริเวณพื้นที่ด้านท้าย downstream ด้านท้ายของอ่างเก็บน้ำนะครับเพราะนั้นก็เราก็คงไม่ได้มองแค่ว่ามันถึงเวลาต้องแค่เปิดระบายตะกอนนะแต่อาจจะต้องพิจารณาในมิติว่าเปิดไปแล้วเนี่ยตะกอนมันมีการเคลื่อนที่อย่างไรใช่ไหมครับนะมันไม่ได้แค่มองแค่ว่าจะออกจากอ่างมากน้อยแค่ไหนนะครับนะมันต้องดูผลกระทบส่วนของท้ายน้ำด้วยนะครับอันนี้เรื่องสำคัญเนาะทีนี้ก็ถ้าสำหรับภาพรวมของประเทศไทยนะครับเนื้อหาในตรงนี้ก็เป็นงานส่วนหนึ่งนะครับของชลประทานบ้านเราเพราะว่าหลายๆอ่างเก็บน้ำก็น่าจะพัฒนาอ่างเก็บน้ำมาร่วมหลาย10 ปีแล้วใช่ไหมครับแล้วก็น่าจะมีปัญหาเรื่องของตะกอนแล้วก็จะต้องมีการซ่อมบำรุงเพิ่มเติมนะครับตัวตะกอนก็ส่งผลทำให้เกิดการเขาเรียกว่าสูญเสียความจุกักเก็บใช่ไหมครับในขณะที่บ้านเราเนี่ยตัวข้อมูลตะกอนเนี่ยจริงๆมีข้อจำกัดเนาะข้อจำกัดพอสมควรเหมือนกันเพราะนั้นเนี่ยถ้าเรามีข้อจำกัดในการเก็บข้อมูลเนี่ยการที่เราเริ่มต้นจากการใช้แบบจำลองนะครับก็อาจจะเหมาะสมกับข้อมูลแต่ว่าจำเป็นต้องตรวจสอบพวกสมมุติฐานต่างๆให้ชัดเจนนะครับแล้วก็วางแผนเก็บข้อมูลที่สมบูรณ์เพื่อจะช่วยให้ตัวงานบริหารจัดการอ่างเก็บน้ำเรื่องของตัวตะกอนในอ่างตรงนี้นะครับก็จะมีข้อมูลหลักฐานแล้วก็รันตัวซิมูเลชันต่างๆได้แม่นยำเพิ่มมากขึ้นนะครับก็คงประมาณเท่านี้นะครับก็ต่อไปเดี๋ยวคงต้องเปิดฟอร์นะครับสำหรับพวกเราสำหรับการถามตอบนะครับก็ท่านใดที่มีคำถามนะครับก็ถามได้เลยเชิญครับดร.นพดลครับขอไมค์ด้วยครับเปิดเสียงหน่อยครับไม่ออกโอเค
Hello again. I think we met during the ONWR. Yep. This is very useful information you're giving us, and thank you for your time. What time is it there?
It is 10:15 in the evening.
Oh, okay. We are feel thankful for your information. I just have a question about the topography shape and watershed shape. Does it have any effect for preliminary setup for the RAS 2025 to be considered? Because in Thailand, the steepness of the longitudinal river profile is different. So when you take into consideration to set up the model, what is the criteria that we should seriously input, and for validation as well, what criteria that we need to be input into the model? Thank you.
So is the question, how does the slope of your river and watershed?
Yes, the shape of the watershed, like reservoir.
So for a watershed model or for a reservoir model?
For the transport model, because some of them have the headwater regime.
Yeah, so this is an excellent question. It goes back to what I was talking about as far as how far upstream does your sediment deposit go? If your reservoir is flat, if you're in the flatlands, I think Pasok Dam is pretty flat. Then you don't have to go as far upstream. What you have to be very careful of, and I think most beginner sediment modelers make this mistake. I made this mistake in my first 3 or 4 sediment models, is most sediment modelers underestimate how far upstream their sediment impact will go. And so in a flat sediment model, you actually have to go upstream farther. But in these steep, and I think Long Prong Plong is kind of one of these steeper reservoirs, but then I know you have some very steep watersheds as well. You don't actually have to go as far up because essentially your reservoir deposit will not go as far upstream, but you will also have much coarser material in those reservoirs. You'll have much more bed load. And so you will almost certainly have a steep delta front.
Thank you. And what is the validation in field that need to be matched with the model to make the model more accurate?
That's my favorite question. One of the things we like to say in sediment transport modeling is that you don't get to call it a model unless you've compared it to some real data. We usually call that calibration or validation. People use different terminology. Sometimes we don't even do it quantitatively, we do it qualitatively. But the best data that you can use, the gold standard, is what I showed you, the repeated cross sections and the change in volume. But remember, sediment isn't all the same thing. And so the other thing you want to know is at each of those points of the deposit, what is the material? Because you also want your sediment model to put the gravel where the gravel goes and the silt where the silt goes. And then another thing that can be useful is a concentration gauge downstream of the reservoir to see if you're getting your trap efficiency right. Because if you know your sediment flux into the reservoir and your sediment flux out of the reservoir, you can make sure that your model is getting the trap efficiency exactly right. And you can balance your sediment budget and compare that to your sediment model.
Thank you.
โอเคท่านใดมีคำถามเพิ่มเติมไหมครับมีไหมยกมือได้เชิญครับเชิญครับ
Thank you very much, Dr. Gibson. I'm Kitiwet from Konkan University. I am very much impressed with your presentation, and I am the one who is the big fan of the HEC software products, the user in Thailand. So I have 2 questions to be asked. The first one is about if I actually have the model set up already based on the earlier version of the HEC RAST, earlier than the 2025, and if I would like to adopt the sediment modeling activities into the existing model, is there any modification or adjustment that I have to do it on my existing model setup? So this is my first question. And the second one is about the parameters. Because if I set up the HEC RAST for the hydrodynamic modeling for the earlier version, And then I accommodate sediment transport in the reservoir into consideration for the model setup. Is there any adjustment for the parameters that I have to adjust besides the parameters that I adjusted in the HEC-RAS hydrodynamic modeling? In this case, what kind of parameters that I have to consider and be very careful with the adjustment of the parameters? Thank you.
All right, excellent questions. The first question, as I understand it, if I'm not allowed to call the old version of RAS old RAS or legacy RAS yet, because many of us still have to use it if RAS 2025 doesn't do what we want it to do. So if I'm starting with a new model, I will always make the mesh in RAS 2025 and then bring it into RAS 7 in order to do my sediment modeling. But the question is, if you have an existing model in 7, well, then you probably just don't leave 7. You use your existing model in 7, you add sediment to it. RAS 2025 can't help you yet. It'll be a couple of years. I'm sorry, because RAS 2025 is great, and I would rather you use it. The second question is, if you are starting with a hydrodynamic model and you add sediment transport to it, what are the sensitive parameters? And this is an excellent question. I said that the calibration question was my favorite question. This one is very close, because one of the things that, again, I think that new modelers do, this question is the mark of a sophisticated modeler, because there are lots of parameters. And one of the things that I see newer modelers do is changing all of them. You don't want to do that. You want to change your parameters that are sensitive and that are uncertain. If your model parameter isn't very sensitive, then you just leave it at your best guess. If you have good data and you have constrained your uncertainty, then you don't want to play around with that much either. But you want to zero in on 2 or 3 parameters that are highly sensitive and highly uncertain. Those are the things you change. There is a problem in modeling called equifinality. Equifinality means that you can put one of your parameters too high and one of them too low, and you can get the right answer, but your model's garbage because it's not real. And so you want to change as few parameters as you can. So that's the context for the answer to the question. I haven't answered the question yet. The most important, if you have a good hydraulic model, I would say that like your N values, your ineffective flow areas, those are the most important things. But if you have a good hydraulic model where those things are good, your bed gradation, so the grain size of your bed, is usually important. That turns out not to be the case in reservoir modeling, because you're just going to dump a bunch of sediment on top of it. So your starting bed material actually doesn't matter that much. So what does matter? The mass of your sediment load and the grain size of that flux, which you almost never have that data. You even if you have good sediment load data, you almost never know how much of it is clay, how much of it is silt, how much of it is sand. So I usually calibrate in 2 stages. I try to change the load until I get the right volume in my reservoir. And then I look at how it's distributed. And I probably don't have the right profile. And so then I'll either add fines or add coarse to move my profile down the reservoir or up the reservoir. And that, the grain size distribution of the flux of the sediment load, is almost always the most sensitive parameter, which means that it's the one that I play with the most to get it to match.
you.
Some excellent questions.
โอเคครับมีคำถามอื่นเพิ่มไหมครับจากท่านอื่นในฟลอร์นะครับถามเพิ่มได้นะครับอาจารย์กิติเวชถามเพิ่มอีกได้นะครับอาจารย์ มีไหมครับน้องๆนิสิตถามได้นะท่านใดที่สนใจถามได้นะครับภาษาไทยได้ครับภาษาไทยได้นะเดี๋ยวให้ดร.ปรินช่วยแปลให้ ถามไหมครับมีคำถามเพิ่มไหมมีไหมเอ่ยเดี๋ยวถ้าไม่มีเดี๋ยวผมถามบ้างดีกว่าสนใจเหมือนกันนะครับDr. Gibson may I ask you some question like you say that the sediment rating curve is very important for the model but if the flow data are available but the sediment load data are limited how should a sediment rating curve be developed?
Is a great question because if you have sediment load data, you're very lucky. And I have been extremely impressed with Thailand's sediment data. For a country your size, you have. I work in a lot of countries. I've worked in over 20 countries. I am in a different country right now, and I have been very impressed with Thailand's sediment data sampling program. But even in my country, the Corps of Engineers district that I started in, of all of the watersheds that we were in charge of, I think we had 3 that had sediment data. You just can't measure all of your watersheds. And so the question is, what if you don't have those data? Well, there are 2 things you can do. You can either, if you already have sediment deposits in your reservoir, you can measure the grain size of those deposits and then calibrate your model by just making up your rating curve until it matches. That's not great, but it's not bad either. The other thing you want to do, and generally I try to do both, is that you go find the closest watershed in shape and slope and size to your watershed that has sediment data and start with that rating curve. Then you have a good place to start with, and then if you're going to calibrate anyways, then you can dial it in from there. And then in the United States, the USGS has developed some regression equations that can help you pick a couple of points off the rating curve. I find those moderately useful. If your country doesn't have those, it's not a huge loss.
Okay, thank you for the answer. ท่านอื่นมีคำถามเพิ่มอีกไหมครับเราจะพอมีเวลาได้อีกสัก1-2 คำถามมีไหมไม่มีละ มีไหมเอ่ยหมดยังโอเคก็ถ้าไม่มีคำถามแล้วนะครับก็คงจบการนำเสนอของดร. Gibson เพียงแต่เท่านี้เนาะโอเค thank you Mr. Gibson for your time and for sharing your experience with us today. Your presentation is very useful for reservoir sediment management in Thailand and in the future if there are some updates on HEC RAS sediment modeling we will be pleased to invite you again and we also hope to welcome you on site in Thailand in the future. Okay, may I invite everyone to give Dr. Gibson a round of applause. ขอเสียงปรบมือ ดร. Gibson อีกครั้งหนึ่งครับขอบคุณครับ Thank you Dr. Gibson.
Thank you very much.
โอเคครับผมก็จบการบรรยายนะครับของดร. Gibson เพียงแต่เท่านี้นะครับก็สำหรับในหัวข้อการบรรยายในเรื่องถัดไปนะครับก็จะเป็นการบรรยายเรื่องการบริหารจัดการตะกอนในขอโทษครับเป็นการบรรยายเรื่องการบริหารความเสี่ยงอุทกภัยด้วยแนวทางโครงสร้างพื้นฐานที่ยืดหยุ่นและการพัฒนาที่ยั่งยืนนะครับ Flood Risk Management through Resilient and Sustainable Infrastructure Solutions using Delft Fields นะครับก็นำเสนอโดยมิสเตอร์มาร์ค เฮกนาเวอร์นะครับเป็น Director Database ของ Singapore Office นะครับครับผม
Okay. Hello. Thank you for the introduction. Yes.
Okay, Mr. Mark, if you're ready, so please, the floor is yours.
All right. Thank you very much. And hello, everyone. Nice to be here. Nice of you to be here to listen to these presentations this morning. We started with an excellent presentation from the US, and I will continue with a presentation on climate resilience through decision support and early warning systems using Delft Fuse. I want to start with the reason why we are working on these kind of decision support systems, modeling exercises, and basically on climate resilient research. Because what we see is climate is changing. So I think everybody is aware floodings become more frequent, more severe. That is already happening, and all the projections towards the future show that this will continue. So climate is changing, so also the risks are changing, and we need to do something about that. If we look into the latest research done through IPCC, so their latest report, they again come with the same conclusion, the same message, that the climate is changing, it has already been changed, and we need to prepare for these changes to come. And some of their main conclusions include that temperatures in the world will go up, and locally they will go very much up. I think Thailand is already experiencing extreme heat at the moment. A couple of weeks ago I saw some worrying messages on heat, extreme heat in Bangkok. So I think this is already happening at the moment here in Thailand and in the region. Also, likelihood of flooding and extreme floods is going up. But at the same time, also droughts are becoming more frequent. And that is, of course, a challenge in a river basin where you have basically you have to deal with both problems at the same time. Be ready for droughts, so you want to store water, but at the same time you want to make sure that you don't store too much water in case of a flood coming. So this is going to be a huge challenge for the water managers of today, and especially of the water management systems of the future. And of course, it doesn't stop at the river basin and not at the rivers. Also, coastal flooding, coastal erosion become more problematic with sea level rise coming. Of course, also Bangkok and the Gulf of Thailand is very vulnerable to sea level rise. So this is something that is again putting another pressure on managing waters in Thailand, but basically in the whole region. And the last point, that weather patterns are becoming more erratic, is another challenge for water management at the time. Because in the past, rainfall patterns, drought patterns were typically predictable. But what we see is that these patterns are changing, and what was normal in the past is not normal anymore. And because these patterns are becoming more erratic, tools like early warning systems and decision support systems become more important. Just as an example of these problems in Thailand, well, everybody here, of course, knows about and remembers the flood in 2011, the biggest flood in Thailand, but I think still also one of the biggest floods in the world in terms of economic damages. But a couple of years later, or actually 2 years later, droughts were a big thing here in Thailand. And of course, there is some kind of relation between the two, because the floods made managers think that we have to prevent that, so we don't fill up the reservoirs to the max anymore, because we need to be ready for the flood. But that, of course, has its downside when the rain is not coming. So this is something that is already happening in Thailand, and we see it in other parts of the world as well. And this is something that is likely to become more frequent and more of a problem in the future when climate is changing. Well, other challenges in Thailand, I think I mentioned already, sea level rise. Southeast Asia in general is very vulnerable to sea level rise. Large parts of the coastline in Southeast Asia are low-lying areas. They are the map that you show here shows in blue all the areas that are below 2 meters of mean sea level already. And that is, of course, only getting worse when the sea is coming up. What you don't see on the map, but what is also typical for Southeast Asia, that in these blue areas, actually a lot of people are living. There's large, big cities close to the sea. So these areas are extremely vulnerable if sea level rise is continuing. And apart from houses and economic and people living, of course there's also the areas like the Mekong Delta where there's a huge agricultural production at risk of drowning. If you then zoom in to urban challenges, because I think in urban situations climate change is typically felt earliest. So what we see is that to be ready for climate change, to manage the water in the urban setting, it's also quite difficult. And that's not only because of climate change, but also because these cities are so rapidly developing that urban planning cannot keep up with the challenges related to water management. But of course, and that's also important, is how to deal with the water, how to manage the water. And that is typically a matter of making sure you have the right data, tools, and well-trained operators to actually be able to operate the infrastructure that you build to cope with these waters. So these are all the challenges that Thailand, but basically many countries around the region are facing when we look into the future. So if we look at these climate risks as a whole, we see that they are dynamic. They are changing all the time. So we see climate is changing, weather patterns are changing, but it's not only the climate. It's also economic growth. It's also population change that is growing. So basically, even if the flood hazard remains the same, the risk is still growing because of the larger economic damages that you can occur with the same floods. So this is also something that you have to keep in mind when you are designing your decision support systems and your operational systems. So basically what we see around the world, and that's also the conclusion of the IPCC, is that we know climate change is there, we know that there's a problem, so basically we need to adapt. And there is a clear need for climate adaptation. One thing that is happening around the world, and it was also shown in the previous presentation, the Google graph showed the dams peaked around 1992. A lot of the infrastructure that we built is aging, is getting old, so they need to be replaced, they need to be adapted to the new situation. And that's a big challenge. That is something that will take time, so we have to also really start developing this now, because otherwise we might be too late. And that also has to do with the fact that this typically takes very long to adapt the situation. What you see here on the right side is a picture from the Netherlands. That's the country where I'm from. And this is all the orange dots are part of the famous Delta works. They were built after the big flood of 1953 to protect the area from flooding due to storm surge. But what you can see is the year in which they were completed. And you see that actually the first part of the Delta works was completed already in 1958, where the last part of the Delta works was only completed in 1997. So it took around, 40 years to complete this whole program of climate adaptation measures. And that is not because we didn't know that it was needed, but it's also because you need the materials, you need the capacity to build these measures, you need to have the companies ready to build this kind of infrastructure at this scale. And that is something that will happen globally when we look into the future. So don't think that you can build this kind of huge programs within a couple of years. So you have to plan ahead, you have to do your adaptation planning. So what we typically do for that is what we call like the climate adaptation planning frameworks. So there's many frameworks out there. So on the right side you see a typical framework for making plans, master plans to prepare your river basin or your country for the future situation. And also Thailand has done that, is doing that. So there's the master plan, the Chao Phraya master plan. Currently some of the plans within the master plan are already being developed and built, and I know that some of the plans are currently being evaluated and hopefully being implemented in the coming years. But it's important that you do this kind of exercises to look ahead and plan for a future that is at this moment still uncertain. But then, of course, you also need to operate. So once you have built your infrastructure, when you've made the designs for your dams, your reservoirs, etc., there is still a need for information and systems that help you to optimize the operation of your water management system. And this is where we see a clear need for decision support and early warning systems. And I think also we should not only we should also realize that this kind of systems are in many cases a no regret to invest in, because studies have shown that investing in early warning systems is the most effective, cost-effective way of reducing risk, especially flood risk in a certain area. So it's critically important that we invest in these frameworks so that you can warn people to get out of areas that are affected by floods, but also to operate your dams and reservoirs in a way that you can maintain as much water and optimize your crop production, for example. So I want to start because this is something Thailand is not the first one to do that, or it's not the only one that has to do that. We've gone through this cycle also in the Netherlands. So I want to say something about the Netherlands, and I'm not sure if everyone in the room is familiar with the Netherlands, but this is a map of the Netherlands, the elevation map. What we see is that a large part of the Netherlands is actually below sea level, with some parts even more than 5 meters below sea level. And in that area that is below sea level, around 9 million people are living. So this is one of the reasons why we in the Netherlands are so looking forward, let's say forward-looking when we talk about water management. And this is why we developed the Delta program to basically protect our delta from flooding, but also looking at other type of problems, because it's not only the floods that are a problem in the Netherlands, it's also the droughts, it's also the water quality. And especially climate change and sea level rise specifically, and more recently also accelerated sea level rise, are for us a big concern, because at this moment we are well protected, we are living behind our levees, living behind our dikes, but what if sea level goes up with 2 meters, or maybe in 200 years it goes up with 4 or 5 meters? Can we still live in our delta, and how does that look like? So to say a little bit about the functioning of the water system in the Netherlands, basically just to make a bit of the comparison, we have 2 big river basins coming into the Netherlands. One is called the Rhine, comes all the way from Switzerland, from the high mountains, and flows into the Netherlands, and the other one is the Meuse. And we have basically two main outlet routes. One through the north via the IJssel Lake, which is also our biggest freshwater reservoir, and one is through the west, through the port area of Rotterdam. And we have issues. So we have drought issues. So this is a picture of the Meuse in 2011. There's a similar picture in 2018, when during very extreme drought condition, the flow in the river goes to practically zero. And we have dry riverbeds. In 2021, that same river looked like this. So this is the floods that happened. The flood in 2021 is actually quite a unique one, because it is happening in the summer. And that is, for the Dutch situation, is very unique. That is actually the first time ever on record that we have a flood of this size in the Netherlands during the summer. Because typically in the Netherlands, floods happen in wintertime, when rain is consistently over long periods, there's no evaporation, so everything is fully saturated and comes down. Summer is typically more classified with localized heavy rainfall downpours, but they will not trigger big flooding in the river. So this was a really unique event in that sense. And this was also a clear signal that climate is changing, because we did the analysis, we looked at the probability of such an event happening in summer without climate change, and that probability was significantly lower than the situation when there is a climate change happening. So yeah, these are the typical issues that we have. So, and of course, drought has impact on many factors. So shipping, agricultural, nature, forest fires, not very different, I think, from the situation in Thailand, in a way. So that's also, I think, in the end, the Netherlands and Thailand are quite familiar, quite similar in the type of problems, and also in the fact that we're both a delta country, or at least the Chao Phraya Delta. You can compare very much with the delta of the Netherlands and the catchment of the Chao Phraya with the catchment of the Rhine. And I think there's a lot of similarities between the two. So there's also a lot to learn from each other in how we deal with that in the future. If we focus a little bit on the floods, because this was for the Netherlands still the biggest trigger to start forward planning, to start developing what we call the Delta program, to start looking ahead instead of only looking backwards. And the biggest trigger was the flood in 1953. So that was a flood coming from the sea that was caused by extreme storm surge, but also caused by huge lack of maintenance of the levees and the dikes. So it's definitely a combination of factors. It's not only the natural hazard that is causing the issue, but definitely also maintenance and preparedness. And it cost around 1,800 people their lives. Many more livestock was killed in the floods, and this triggered the development of the delta works, so the storm surge barriers and the dikes along the coast. So what happened then is that a lot of attention went into the coastal protection. So when we closed up the coastline with the delta works, we thought we were okay, and then in 1993 and 1995 the threat came from the rivers. And then we again experienced a quite severe situation, although it didn't in the end lead to a big flood, but it was very close, and that would have been catastrophic given that the rivers would have flooded areas that are 7-8 meters deep and would have flooded that area for weeks or months. But again, so luckily we were protected, we were safe that time, and we could start the whole Delta program for the river, including the Room for the River program, making more space for the water in the big rivers. And then in 2021, I already said, this summer flood that triggered another rethinking of how we need to protect. So our focus was first on the coast, then on the big rivers, And then we realized, but there's also some smaller rivers that are affected by flash floods. So also here, this now triggered a new research program and a new development program around flash flood readiness, basically. So what we now are doing to prepare for climate change is what I said. We look to the projections for sea level rise, extreme rainfall, etc. But we realize because climate adaptation takes so long, we need to look further ahead. And when you look further ahead in the climate projections, especially sea level rise projections, there are some worrying projections. Some projections say that if we don't stop climate change, or not enough, sea level could go up with 4, 5, maybe 10 meters within the next 200, 300 years. And that seems long away, but if you think about 10 meters of sea level rise in front of your city, Bangkok, what do you do? How do you deal with 10 meters of sea level rise in Bangkok? Well, that is the question we now have in the Netherlands as well. So we are now looking at what we call these adaptation pathways and really forward-looking to all kinds of new strategies of dealing with extreme sea level rise. From building a completely new coastline, not very different from, I think, the plan on damming the Gulf of Thailand, which is, I'm not sure if it's still in the plans, but I've read about it. Well, it's something that we are now looking at. But there's other solutions as well that we're investigating, including also scenarios where we are going to pump a lot of the water. And this will also require a huge thinking on how are we going to operate this kind of systems. So to do that, we typically make use of our models, our platforms, to first get a good idea of what can happen. And so we use the models, the national models that were developed to support national level decision making. We use that to understand a little bit what can happen in different scenarios. Then we can make also informed decisions on how to deal with this kind of flooding. So in this scenario is a big flood on the River Rhine. The flooding happens in Germany, so but overland the water will come to the Netherlands as well. This is one of the big important scenarios for our design criteria of the levees in the Netherlands. And this kind of information, of course, also provides very valuable information for operational decision making. If you need to evacuate people, you know what kind of scenarios are likely to happen. So we use this information also in our operational forecasting systems. It's not only looking at the floods. So this simulation, the color coding is not flood depth, but this is the risk level. And that is, of course, the risk is a combination of flood depth, flood velocity. So it's looking at different aspects of the flood to understand where are the risks highest, and which areas do we need to protect first, or do we need to evacuate first. So this is all kind of studies we do with our national models to prepare and to use in operational decision making. And that operational decision making is something we do on a daily basis. So we have what we call the Water Management Center of the Netherlands. It's the organization responsible for 24/7 monitoring and forecasting of all the water systems in the Netherlands. And they are also the ones that issue warnings and coordinate actions. And they also do trigger the control of our main operating gates and barriers. And yeah, so one example of that is this barrier. So this is I don't know who of you have ever been to the Netherlands. So this is the Maaslandkering. So this is the last delta work that was finished. This one is operated based on the forecasting, the forecast that is done in this water management center. It makes use of weather forecast, hydrodynamic forecast to make sure that we close it at the right time to protect the hinterland when needed. But that, of course, requires a lot of other insights. So this is not the sea, but this is coming from the Rhine, from the upstream catchment. So also this platform we use to monitor floods coming in to the Netherlands from our neighboring countries. So this also requires, of course, good collaboration with our neighbors, sharing of data, sharing of information to make sure that we are well informed if something is coming through the rivers to the Netherlands. Because this river, what coming in, is our biggest inflow into the Netherlands, and is also our biggest risk for flooding in case. So we integrated that all in the platform. In the platform we also summarize it for easy decision making. So it's a very boring day because everything is green, so nothing is going wrong. But this is basically to get a very quick overview of the situation, pulling all the data, all the information, all the models together and make it into actionable insight for decision makers. So the success factor of this daily operational system is that we manage to integrate everything into a central data and modeling framework. And that is, I think, really key. Have all the information come together in a systematic way with easy to understand visualization. Also, the sharing of data, I think, is critical. What I already said, the data coming from our neighbors, neighboring countries is very important for our decision making, but also the sharing between the national level and the regional level water managers is of critical importance, because we have organized our water management in the Netherlands at the national level, but there's a level below, the regional level. They drain water to the national waters, to the national rivers, but you have to know in times of emergencies or in times of critical situations, how much water are they going to drop into the rivers, and can the river actually handle that additional amount of water, and can our pumping stations, for example, deal with those situations. So therefore it's regulated that data and information is shared between all these organizations. We also realized that research and development, continuous research and development, is also a critical element of success. Keeping ahead of the game, making sure you make use of the latest insights. So nowadays, AI, machine learning, all that kind of things are now already being picked up in the R&D and immediately brought to operations to utilize it for real time and real decision making by our decision makers. And I think the last point is actually also quite a critical point of success, is that the whole system is part of the, let's say, the critical infrastructure of the ministry. So they also realize that you have to maintain your critical infrastructure, and you need to make really clear arrangements and agreements with the developers, the users and the maintainers. So those are typically written down in what we call the service level agreements, and by doing that, it's a formalized process, but it makes it very clear what are the responsibilities of each organization in terms of making sure that this critical infrastructure is up 24/7. So I'm going to zoom in a little bit to that central forecasting platform, because that is in the end what we are here about the software. So basically the software that we use for that central forecasting platform is called Delfuse. And Delfuse sits in this blue box. So in any water system you have measurements, you can, based on the measurements already, issue a warning. I mean, that's how it has been done all in history. But what makes these forecasting systems useful is that you can digest a lot of data and information. You can combine it with models, hydrological models, hydrodynamic models, and all with the purpose to increase the lead time. Because in the end, that is what you want. You want to have sufficient time to make critical decisions. Critical decisions like, am I going to evacuate a neighborhood or a city? Am I going to put sandbags to protect a part of the city? So those kind of decisions, you want to make them in time. You don't want to be too late. And that is all to do with this, this timeline basically. So it all starts with data collection. If you have no data, you have no clue what is happening. So data collection is still a critical, important element of any early warning system. So the data, typically flow data, rainfall data, etc. And then, of course, you need to evaluate that data. And evaluation is like, how much, what is the return period of the rainfall? You can use models to interpret that data into like flood maps. And then after evaluation, you can say, hey, a certain threshold is crossed. So we realize there's a threat. So that is the moment that the forecaster typically sends a notification to his or her boss or to the decision maker, like, hey, we see something coming, we might need to make a decision. Then, based on that notification, people in charge will do the actual decision making. And the decision is typically we do something or we do nothing, and if something, what is then what we do. And that is when the response begins. That's when basically the fire brigade is sent to the street, or the military is sent to the to put sandbags, and each of these actions has a certain time period, and to find, let's say, the value, or to optimize the value of your early warning system, you have to realize, like, what are the actions that you can take, how much time does it need to take that action, how much time does it take to come to a decision, and basically that sets your design criteria for your operational system. So in Fuse, what we do, the main thing is to help the forecasters and the operators to streamline that process. Because if you have to collect all the data yourself manually, that you already lose valuable time in the process. So basically, Fuse is there to automatically and on a daily basis or hourly basis or even 5-minute basis take in the data, process the data in a standardized way, and presenting the data to the forecaster in a standardized way. You can even set up automatic reporting, automatic warnings. So that's all possible within the platform. Then within the platform, you can combine this data with your models. That can be flood models, but it can also be water quality models or sediment models that we heard about just now. So it depends on what kind of decision support or early warning system you're making, what type of model you want to integrate. And then, of course, you translate all that information together into a forecast of something that you are interested in. In this case, this is a flood map, but you can also do reservoir inflow forecasting, for example, and you translate all that information on the left automatically into the desired outputs. And that is what Fuse is all about. So in summary, it's a data and model integration platform built for 24/7 operational systems. So it can run automatically, it can trigger workflows automatically, you can schedule those. So basically to really have the forecaster do as little as possible, let him or her focus on the actual analysis of the forecast. And yeah, so it's there to organize your data and really go from input to forecast dissemination automatically. It's data-centric, so the database is, I think, the critical important, and it can digest a lot of data, radar data, numerical weather prediction data, sediment data, water quality data. Everything can be combined in that one database. And you can basically configure the whole system yourself. It's, you have to learn, of course, how to do that, but it is completely configurable. So I will show some examples later on. You will see that every application looks different because different user requirements, different models. But that is under the hood, it's the same platform. And then, of course, yeah, it's open, modular, so different type of models. So the HEC-RAS models that we discussed just now can also be integrated into Delfuse. That's actually already being done at the moment for RID in the RID SWAMP system. It's free to use, so that's also, I think, nice for if you want to start up this kind of systems. There's not a huge investment cost other than that you need to invest time to learn how to use it and how to do it. Yeah. And it's used globally around the world. So here's a map showing so where currently Fuse systems are being used and implemented, and we have different type of applications. So we have really flood early warning systems. That was what it was originally all about, flood early warning. But nowadays we also use it for reservoirs, reservoir inflow forecasting or optimization, water quality modeling and forecasting. We use it for dike strength monitoring and forecasting, groundwater, etc. And this is, yeah, a screenshot. So this is all Delfuse, all different countries, all different types of systems. No need to go into that. So basically, this is the yeah, the overview of Delfuse at the heart. So at the top we have all the external data, external forecast data. You import that typically into Delfuse, into the database, and there's a lot of like data processing included in Delfuse. So if you want to do, for example, from hourly to daily rainfall estimates, or you want to do spatial averaging over your subcatchments, all that kind of processing can easily be done within the platform and can be optimized also. So every time you get your rainfall in, you can automatically then get your rainfall at your subcatchment level. So it's a continuous cycle of processing that you can do. And then, yeah, we have the models I already mentioned. So different type of models for different type of applications. And then, yeah, you need to export the data or disseminate the data, and there's also many different ways of doing that. Delfuse has its own interfaces, but it also has an API, so you can also build your own web applications or your own phone applications that call the API. So, and we've seen many flavors, many types of applications already built on top of the Delfuse ecosystem. Yeah, so this is a summary again. Good to know. So already for I think somewhat around 10 years, we started also with the deployment of Delfuse in cloud infrastructure. So for example, in Azure or Amazon cloud systems. Not every client likes that. Some clients want to have the data still on-prem. Is also possible, but we see that more and more clients are actually very attracted to running these kind of systems in the cloud because it allows for scalability of the solution. And I'll come to a good example of that later on. It's a community-based model, so that means that we have a strategy board comprising of different users of the platform. So for example, Environment Agency in the UK, the Bureau of Meteorology in Australia, Rijkswaterstaat in the Netherlands, they are all in the strategy board, and they jointly decide like in which direction we should continue the development of Delfuse. That makes that what we do and how it develops stays relevant for our users. And there are many partners that can also help with the implementation. One of our partners here in Thailand, Panya, I'm not sure if they are here in the room, they will tell more this afternoon, I understand. So there's many partners that can help you also with the setup of these Fuse systems. Some examples of the Fuse community, the user days in different locations. We had some in Thailand actually as well, a couple of years ago in Singapore. So also closer by home, you can meet the Fuse community. As I said, I wanted to show a couple of examples. Well, the Netherlands, I will go quickly because we've talked already about it, but basically what we have is we have a set of applications looking at different aspects of the water system. So we have basically 5 applications talking to one central database. So because that one central database is where all the information is stored, and that's also how different forecasters can easily sort of talk to each other. They look at the same data even though they look at a different application. Because we have forecasted that specifically zoom in to the coast. We have forecasted that specifically zoom into the rivers. Well, those two meet each other, and in that area, what we call the Rhine-Meuse Delta, is where things become really complicated, because it's impacted by both the river and the coast. So that has its own application with its own tools and models to analyze the forecasts. And then we have for the lakes and for the canal systems, we have applications. I'll skip this one. So this is just an example of the early warning platform for the Rhine. We look typically ahead 14 days based on the weather forecast. Nowadays it's very normal to also look at ensemble forecasts because we have a deterministic forecast. You can basically be certain that your deterministic forecast is wrong. So it's better to know that how wrong you are likely to be. And that is typically visualized through ensemble forecasts. This is another system. So this is basically, it uses the inflow from the Rhine as an input. And then within the Netherlands, we typically can divert the water. So we have regulators in the water system, and this system helps, based on a real-time control optimization algorithm, to steer the water in the right direction automatically as much as possible. And again, including very simple, understandable visualizations, so that an operator or a water manager immediately can see what is happening in the water system. So the storm surge forecasting, that is then the third component. This is why. So these are pictures of that big flood at the time. So what we did there is we built a 2D and a 3D hydrodynamic model using Delft 3D. And that is used to do coastal modeling and coastal forecasting. And what we basically use it for in this application is to simulate storm surge. Because the storm surge is when things become critical. So here we have a coupled model, a hydrodynamic model, and a wave model. And they run operationally on a daily basis or on an hourly basis actually to give the insight in storm surge. And this is quite important to run it very frequently because I don't know how that is here in Thailand, but in the Netherlands, wind forecasts are very difficult ahead of time because the weather patterns are not stable above Europe, so they can shift very quickly. So very quickly, storm surge also projections can also differ very quickly. So basically we say storm surge can only be accurately simulated 6 hours in advance. But by using ensemble techniques, we can already get a feeling of potential forecast of a storm surge. So this Maasland barrier is one of the important and critical gates that protects in case of a storm surge. And this gate is fully operated based on predicted water levels. And that is That is quite special because in many cases around the world, storm surge barriers are operated based on observed water levels, but this one, because they're behind the gate is the port of Rotterdam, and behind the gate is the Rhine flowing into the sea. So basically, we need to know how much water is forecasted to come via the Rhine towards the coast. Because if too much water comes from the land, it might pose a structural threat on this barrier. And in some cases, it's actually then better to not close than to close the barrier. So we use that information, the forecast information, and this is then typically how that looks like, the cycle for closure. But basically, the key of the story here is that we use forecasted water levels using this automated forecasting platform to predict when the barrier will close. And if it needs to close, it's a fully automated process. So that's maybe also good to realize that this barrier, it will close if the forecast says it has to close. There's no manual button to push. There's only a manual override button to push in case of an emergency. So then we go across the channel. For us in the Netherlands, at least, we go to the UK. So the UK was one of the first adapters of Delfuse. So that's the UK Environment Agency responsible for the national flood forecasting. So here, basically, together with the EA, we developed Delfuse into a mature and into the mature platform it is nowadays. And basically, it's it's doing both. Inland flood forecasting, so for the rivers in the UK, as well as for the coast. And the coastal model, again, like we do in the Netherlands, is used to operate, in this case, the Thames barrier. So again, this forecast automated forecast information is used by the Environment Agency to basically close the barrier in case that is needed. Some interesting features here. So the UK has many different weather products that they are using. They are also using what they call spatial modifiers. So they want to be able to play around. What if the rain falls somewhere else? So they can basically use the platform to move the rain around and test scenarios like whether a certain rain event could cause some problem elsewhere if the forecast is not accurate. So basically what we then do, based on thresholds that were set by the Environment Agency, we can automatically generate warnings. So that is the map that you see on the left. And those warnings also trigger automatically, like a warning to the public for a specific area that might be flooded. Interesting also, there's also a feedback loop. So we have a collaboration with Floodtex. Floodtex, they analyze social media on keywords like floods or whatever, and that information proves to be very valuable additional information to see where things are actually happening. Also there where you don't have formal observations, maybe people take a picture or put something on Facebook, and that information we also feed back into Fuse, to as a sort of a secondary data source about flood warnings in the UK. I think what is quite spectacular in this system, it's the first system that we migrated from an on-prem system to a cloud system, and the reason for that was that they wanted to be able to scale up when needed. And the UK is, well, it's quite a big country. They didn't want to run their flood models 24/7 because that is computationally quite heavy. That means a lot of compute power, a lot of computers that you would need, and 90% of the time those computers are actually not needed. So basically what they want is they want to say, well, We only want to trigger those models in case there is something happening. But then at that moment, we need to have the answer fast. So what we set up here is basically a system that runs in the cloud, and based on automatic thresholds, crossings, we automatically scale up the whole situation from 25 to 150 servers running all the flood simulations simultaneously to get the answer fast. So this is the quite advanced system in that case to make use of that advanced the cloud infrastructure. A completely different type of system is for a municipality in South Africa, and this is it's all about coastal flooding. So here what we do is we integrate coastal models. So we start with like a Delft 3D model for water levels around the coast. We couple it with wave models, wave runoff models, XPeach, and then a flood inundation model to very quickly get an indication on which part of the city might be flooded in case of a hurricane coming by. And that happens quite frequently in this area of the world. So this is then sort of the schematic of how that looks like. And every time for each domain, we use a model that is computationally efficient. Because again, in operational forecasting, time matters. So you don't want to wait for hours and hours to get your answer. So basically, we make use of each model for each domain where it is sort of best suited for that, and we connect all these models together in Fuse. So Fuse is taking care of the order in which these models are running and preparing all the data going from one model to the other. And this is then how that looks like. So this is an animation of the flood model for a specific flood that happened a couple of years ago. So this is then all integrated into a Delft Fuse platform with a web interface that we can then use to disseminate the information and the data to decision makers that need to do something with that information. For example, to say whether the beach or a road is at risk, and when that would be at risk, and to help them also prepare road closures or diversions and things like that. Well, this setup, we are experimenting with other types of applications as well. So one of them is swim safety, so a swim safety forecast. So this is a beach city that also attracts a lot of tourists that like to go swimming, but the rip currents are actually quite dangerous in this area, so swimmers get into problems when they go into the water. With the models that we have developed, integrated in the platform, we are now experimenting whether we can also give a rip current forecast that can be used, for example, by the lifeguards on the beach to close or to open the beach. Another typical of another coastal application that might also be relevant for Thailand is an application that we're currently developing in Singapore. So this is a coastal model where we look in this case to salinity, also salinity intrusion in the rivers there. For this we use a detailed 3D Delft 3D model, and basically by integrating that model operationally into Delft Fuse, we run it, it's always available, so you can always look at the results, both spatially, that's what you see on the left, but also in time, so you can also see how salinity goes up and down in time, but because it's a 3D model, you can even also look at the vertical profiles of the salinity. So this is one of the use cases in Singapore. That same model we also use for water quality purposes, and in this case what we are doing is to integrate a spill model. So in Singapore, of course, the port area, there's a lot of ships, so there's also from time to time there's an accident like an oil spill or a chemical spill, and what they then need to know very urgently is like where is the spill going to. So this again fully integrated into Delft Fuse. through the web interface, the user can say, hey, the spill was here, it was so much oil, it was so much other chemicals, and then within 5 to 10 minutes, they have their first answer, like where the oil spill is moving to. And this is a simulation from an oil spill in 2024, and the model is very accurately reproducing the spread area of the oil. But the nice thing about it is it's integrated in this platform. You have the data always ready, so you can very quickly act, and the user can very quickly get a first result to make decisions. Another, and this is I think one that is quite relevant also here for Thailand, is reservoir optimization. Optimization is basically the art of coming to an optimal solution for your problem. While you have different goals that you want to achieve, typically also conflicting goals that you need to achieve. Typical example is you want to maximize energy production, but you want to reduce flood risk. You want to promote ecological flow in the river downstream of the reservoir. You want to maintain water for irrigation. So all these goals, they might be conflicting. And it's difficult to optimize these kind of problems, and that's where a model predictive control model might be helpful, that helps you find the optimal solution. Well, these figures here show a little bit the complexity of this kind of optimization questions, because mathematically finding an optimum, the real optimum in a multi-dimensional space is quite complex. But that is where RC tools, the toolbox that we developed at Deltares, comes in, and it's actually a very good combination with Delfuse, because Delfuse, as I said, prepares all the data, streamlines the whole process, and RC tools can then use the data immediately to come up with an optimal strategy. So Delfuse can be used for flood forecast, but also then the inflow forecasting, how much water comes into the reservoir. Then RC tools can be used for hydropower scheduling or dam safety goal setting. You can also set goals on water quality or water allocation, and this is then all integrated in Delfuse. And one of the applications of this combination of Delfuse and RC tools is for Niagara Falls. So Niagara Falls in the US, it's actually quite a complex system with quite a lot of goals that they want to achieve. One of them being that it is a very nice tourist attraction, so there should be sufficient water coming through the waterfall, so that the tourists are not very disappointed. So that's one of the goals in the system, apart from the fact that they also want to generate energy from the system. So there's different flow control. So basically, a flow control on does water need to be diverted? Is there too much water in the system? Do we need to divert it? There's a decision to be made. Is there sufficient water to pump up the water to the pumped storage situation? And then there's a decision on how much energy can we actually consume or generate in the system. So all these different goals are then fed into the model in combination with all the real-time data that Fuse is getting from all the sensors to basically come up with the optimal control situation. So here, this is an example, and what is nice about this system, so we basically have one platform, one model that then can be used for very different applications. So we have the same model with different goals and different settings can be used for hydropower scheduling. So that is something for the next week, or maybe the day-to-day scheduling. But if you feed seasonal flow forecasting into the model, you can also start doing your business planning, long-term ahead planning of your system. You can also use it if you collect data over many years. You can analyze your system and can find maybe afterwards ways to further optimize your control of the whole system. And if you feed in high resolution data like hourly or 5-minute rainfall data, you can maybe even use it to within the day or within the hour find the maximum power generation scheme for that moment in time. So this is how that works. The last example I think I want to share is for again a different use case of Delfuse. I'm going to run a bit over time. I'm sorry. Yeah, is the Murray-Darling Basin in Australia, and here Delfuse is used for a completely different type of application, but it is an application that we see happening in many countries and many organizations that have the same issue. So the Murray-Darling Basin is actually a very large basin. It runs, as you see on the map, over 4 different states. So each state in Australia has their own rules and regulations and jurisdictions. Within each state, each valley or each sub-basin can have their own jurisdiction. So and they all need to come up with a with a planning strategy for how to deal with the water in the basin, both for the short-term planning but also for climate adaptation planning. So here what we see is that basically there's a lack of coordination throughout the basin in terms of the modeling approach, etc. And that makes that basin-wide studies are very complex. And especially also for users in the downstream part of the basin, this becomes quite problematic if they don't know what their neighbors upstream are doing and how that might impact their operations downstream. So this project that we worked on was basically developing a methodology within Delfuse to share scenarios, connect different scenarios and models from different users, different organizations together in one platform, so that the downstream user knows what kind of models and scenarios are available for the upstream part of the basin, and they can decide, well, hey, I want to do a planning study based on this scenario, so I need to take the results of this model or that scenario from my upstream neighbor to have a consistent story and a consistent analysis. So this is not so much of an operational system. Oh, sorry. It's more on how to collaborate and still integrate everything in that one platform and that one shared information system. And I think this is also something I was just talking. So I know RID also has like the basin-wide, but also regional offices. So how to connect those to each other? I think that is a challenge we see everywhere, and this might is an option to help with that. So those were some examples of Delfuse being used around the world for very many different applications. If you go back to the Chao Phraya, I think we discussed in the beginning, there's the master plan for the Chao Phraya currently being evaluated and implemented. But there's, of course, at some point you need to go from strategic planning to operational management of the system. So then more these operational questions come to be, like how do we actually operate our dams and reservoir within the larger scheme? Maybe how many crop rotations can I do every year? Or maybe this year is different. How can we protect from flooding? So these are more operational questions that require operational data to be combined with the operational models. And for this purpose, well, together with Panja and RID, the RID swamp system started. It's a hydrologic and hydraulic models integrated into Delfuse, with the idea to slowly build up the knowledge base from upstream to downstream to come to a sort of a basin-wide information system. And currently it's focusing on hydrological and flood forecasting, using also the models that were just presented this morning, the HECRAS models for the flood modeling. But if we look ahead, I think there's a lot of opportunities to expand the RID swamp, and I think we hear a little bit more about it this afternoon, also on the ideas for expanding RID swamp. But I think showing, given all the examples that I gave this morning, it makes sense to keep sort of, to integrate those into this central platform, because in the end, a lot of the data that you need for the different applications is shared, and it's always good to share the data as much as possible. Last part, because in the end, let's say, we can talk about the technical parts of this kind of systems, models, early warning systems, etc. But there are other aspects that are also important. And first of all, I think the goal of these kind of systems and models is to improve decision making. And decision making is typically done in when the decisions are based on mutual understanding of the situation. So you need data and models and systems that help understanding the system so that everybody agrees on the current issues, problems, and potential solutions. And that means that the data that goes in and the models that you go in and the methods that you use should be more or less generally accepted. So that is something that I think is also important. It's really a community effort to make better decisions from government agencies, research agencies or institutes, and the consultants that help you build the system, that everybody has that same knowledge base to work from. And then in the end, maintenance is quite important. Because once you start this journey to develop this platform, it's critically important to keep it up to date, to maintain it, and to slowly improve it, to keep improving your decision making. And then it comes to not only technical challenges. So it is not just about the data or the software or the models. In the end, it's also about the people and the organizations that you work with. So to give an example, so in the Netherlands, we have the Dutch water law. And in the Dutch water law, a lot of these things are sort of stated, like what are the requirements that our government needs to fulfill in terms of water management. And that comes down to developing strategies and guidelines in implementing these goals. Then you need, of course, the organization to be ready to work with it. So you need to have qualified staff. You have to you need to have some strategy, some vision behind it. Some policies and some rules to enforce some of these changes. And then, of course, you have the whole operational process, which might not even be a technical process, but more like who is responsible for what. And all those circles, they in the end determine how the technical system looks like or should look like. So this is also from a presentation by Golding et al. Basically also stating that early warning, it's not only a technical challenge. Of course, we think often a operational system is a technical system, but it starts with observations, and of course there's sensor technologies but also maintenance of those sensors, etc. Then we have weather forecasters; they have their own technical challenges. Then the hazard impacts, warning, decision. But the further we go to the right, the least it's about the technology. So basically, we go almost into what we call behavioral psychology. Like, how do you actually get people to move out of their house if they need to evacuate? So you need to get those people also in the room to design and systems that actually make an impact. And maybe actually when we are designing our early warning systems, we might also want to take the route from the right to the left. In the end, it's the decision that is important. We want to make sure that if a flood is happening, that and a decision is made, that we want to optimize that part of the cycle. And everything that's coming to the left is there to support that decision. So we can invest a lot of time in optimizing from left to right, but and if we forget the right side of this picture, we can still have a system that is not effective, and that would be a shame, of course. I will skip this one because I think I'm already quite over time, so I will end with this slide. So yeah, I think my key takeaways say, well, climate is changing, so we need to adapt, and I think that decision support systems and warning systems are a critical part of climate adaptation. So they are no regret in terms of early warning. It can really reduce risks in areas that are vulnerable, but we actually also need those systems to effectively manage our water system. So I know that in the Chao Phraya and the master plan, a lot of plans are going, a lot of new regulators are being built, pumping stations being built, etc. But if we don't know how to manage those investments become useless. So those investments need to go hand in hand with optimized decision support systems to go hand in hand. And I think with the RID swamp system that RID started, I think there's a really good starting point to slowly start building up this whole decision support and early warning platform at basin level, and slowly move towards a multi-purpose decision support system when you start integrating not only flood models, but also maybe water quality or salinity intrusion modeling and things like that. And then the last point, also I find very important that once you start this journey, it's important to take care of it. So maintenance, support, that requires dedication, that requires also continuous funding. I mean, these systems don't stay alive by themselves. They need to be updated, even though if it's just for cybersecurity issues. So even you have your own laptops on your desk. They have every month they have Windows updates being pushed to your laptop. It's critically important in this time to do that. And the same goes for these systems. We need to maintain them and we need to update them. And then the last one, it's also requires the organizational capacity to manage this kind of data, models, and integration platform. And that is, of course, that is also a journey, and that is something something that's continuously done. And I think a lot of people that sit in the back of the room, the students, are going to be part of that story in a couple of years. So you learn and you keep learning on the importance of these systems and working with data, working with models, and that is how you basically build up the capacity as an organization and a country to develop and maintain these systems. And I think that's where I want to end my talk. Sorry for running a bit late. Yeah.
Okay, thank you very much, Mr. Mark, for your presentation. Before we move to the question, I would like to briefly summarize the key point in Thai for the audience. Okay, ก็ขอสรุปภาพรวมเนาะสั้นๆเดี๋ยวก่อนจะถามนะครับแล้วก็วันนี้ก็ที่มิสเตอร์มาร์กนะครับที่นำเสนอเนาะก็จะเห็นว่าโจทย์ใหญ่นะครับที่ทางที่เราพบเห็นกันเนี่ยคือเรื่องของตัว climate นะ climate risk เนี่ยก็ทำให้ทุกอย่างมันกระทบหมดเนาะภัยแล้งน้ำท่วมน้ำทะเลหนุนอะไรต่างๆนะครับแต่เนี้ยก็จะบอกว่าเขาบอกว่ามันไม่ได้เกิดจากแค่เรื่องของตัว climate อย่างเดียวจริงๆในฝั่งของมนุษย์เองนะครับเรื่องการเปลี่ยนแปลงการใช้ประโยชน์ที่ดินตัวเมืองประชากรเศรษฐกิจเนี่ยมันเปลี่ยนไปด้วยกันนะครับเพราะนั้นบางทีเราจะบอกว่าน้ำท่วมเหตุการณ์น้ำท่วมเหมือนกันแต่ว่าลักษณะของการเปลี่ยนตัวเมืองหรือที่ดินเนี่ยมันก็ทำให้ผลกระทบมันต่างกันนะครับทีนี้ก็ ตัวอย่างที่เขายกชัดเจนเลยนะครับว่าของไทยแลนด์เนี่ยของประเทศไทยเราเนี่ย2011 เพิ่งจะท่วมหนักไม่ใช่เหรอ2013 กลายเป็นแล้งกันทั่วบ้านทั่วเมืองนะครับเพราะฉะนั้นตัว flood กับ drought นะครับน้ำท่วมน้ำแล้งเนี่ยมันไม่ได้เป็นปัญหาที่แยกจากกันนะครับในพื้นที่ลุ่มน้ำพื้นที่ใดพื้นที่หนึ่งเนี่ยมันอาจจะเกิดทั้ง2ส่วนนะครับแต่มันอาจอยู่แค่คนละช่วงเวลาวันนั้นเนี่ยเรื่องของการตัดสินใจตัว decision เรื่องของการเก็บน้ำการพร่องน้ำการระบายน้ำการเตือนภัยเนี่ยมันจะมีผลต่อเนื่องข้ามปีข้ามฤดูกาลกันนะครับแล้วก็ประเด็นที่เขานำเสนอคือเรื่องของตัว infrastructure เรื่องของโครงสร้างพื้นฐานเนี่ยแค่โครงสร้างพื้นฐานอย่างเดียวมันไม่ใช่สิ่งที่พอเพียงสำหรับในการลดความเสี่ยงทุกอย่างให้เป็นศูนย์ได้เนาะคือต่อให้เรามีเขื่อนมีคันกั้นน้ำมีประตูมีปั๊มมี barrier ต่างๆเนี่ยสิ่งสำคัญคือ decision support system กับ early warning system นะครับคือตัวที่ช่วยสนับสนุนการตัดสินใจกับช่วยเตือนภัยล่วงหน้านะครับซึ่งจะช่วยให้ทางผู้ปฏิบัติงานอย่างน้องๆเนี่ยวันข้างหน้าถ้าเราเข้าไปปฏิบัติงานในช่วงภาวะวิกฤตเนี่ยพวกเราเองเนี่ยก็จะได้เห็นสถานการณ์ล่วงหน้านะครับเพราะฉะนั้นถ้ามันมีระบบที่ช่วยมองเห็นพวกนี้นะครับมันก็จะช่วยให้พวกเราเนี่ยตัดสินใจก่อนเกิดวิกฤตได้นะครับทีนี้ประเด็นที่ของทางเดลฟ์ฟิลนะครับที่เขามาทำเป็นตัวเรียกว่าเป็นแพลตฟอร์มเนาะเป็นแพลตฟอร์มที่เป็นอินทิเกรตแพลตฟอร์มนะครับซึ่งจะเห็นว่าตัวแพลตฟอร์มตัวนี้คือสามารถอินทิเกรตตัวแบบจำลองเนี่ยนะครับไม่ใช่แค่ตัวเดียวแต่เขาอินทิเกรตหลายตัวที่เป็นจุดสำคัญเนี่ยแล้วก็สามารถรวมแล้วให้ข้อมูลที่เป็นเรียลไทม์นะครับตัวทั้งพวกพวกอะไรrainfall forecast นะครับพวกวัดระดับน้ำพวกแบบจำลองไฮดรอลิกอะไรต่างๆเนี่ยนะครับก็รวมมาอยู่ในแพลตฟอร์มเดลฟิลนะครับแล้วก็มีแดชบอร์ดนะครับที่ก็จะช่วยให้การจำลองต่างๆนะครับผ่าน workflow หรืออะไรต่างๆเนี่ยทำให้เรามองเห็นนะครับข้อมูลร่วมกันเป็นการแชร์ข้อมูลร่วมกันได้นะครับแล้วก็จากประสบการณ์ที่ทางเนเธอร์แลนด์นะครับนำเสนออย่างของเนเธอร์แลนด์เองหรือของประเทศอื่นเนี่ยก็จะเห็นว่าจริงๆตัวระบบที่เอามาใช้ในการบริหารจัดการน้ำในระดับประเทศเนี่ยคือมันก็มีทั้งส่วนทั้งตัวข้อมูลแบบจำลองขณะเดียวกันทางฝั่งการจัดการก็ต้องมีศูนย์ปฏิบัติการเนาะศูนย์ปฏิบัติการมีกระบวนการทำงานมี workflow ต่างๆเขาเรียกว่าเป็น 24/7 ก็คือตลอด24 ชั่วโมงใน7 วันเลยถ้าเกิดเป็นภาวะวิกฤตนะครับแล้วก็ตัวอย่างที่ของไทยเนาะที่ตอนนี้ที่ของทางเนเธอร์แลนด์มาใช้กับไทยเราเนี่ยก็คือตัว RID Swamp เดี๋ยวช่วงบ่ายนะครับช่วงบ่ายก็จะมีของทางดร.ศิริลักษณ์นะครับท่านมานำเสนอของ RID Swamp เพิ่มด้วยนะครับก็เข้าใจว่าปัจจุบันน่าจะยังอยู่ในส่วนของตัว flood อยู่เนาะแล้วก็จะขยายไปมิติเรื่องของตัว drought ความแห้งแล้ง water quality กับมิติอื่นๆได้ด้วยนะครับคือมันเป็น integrate platform ที่รวมอยู่ในระบบเดียวกันได้นะครับแล้วสิ่งสำคัญที่มิสเตอร์มาร์กบอกก็คือส่วนที่ความสำเร็จเนี่ยคือมันไม่ได้อยู่ที่ตัวซอฟต์แวร์หรือฮาร์ดแวร์หรือ Data อย่างเดียวเนาะอยู่กับคนกระบวนการทำงานนะครับเมื่อกี้มีเรื่องของตัวนโยบายองค์กรด้วยเรื่องของตัวการแบ่งปันข้อมูลงบประมาณฝึกอบรมคือมันไม่ได้เป็นแค่ตัวระบบ forecast system ที่เราซื้อครั้งเดียวจบนะครับแต่มันจะต้องตามมาด้วยตัวของการ maintenance เรื่องของการ support เรื่องของการ upgrade training ให้มัน up to date ให้มันทันสมัยขึ้นอยู่เรื่อยๆนะครับเพราะนั้นเนี่ยก็ถือว่าเป็นตัวแพลตฟอร์มใหม่ที่ไม่เรียกว่าใหม่นะเรียกว่าเป็นตัวแพลตฟอร์มที่มีศักยภาพแล้วกันนะครับศักยภาพในการช่วยให้เปลี่ยนจากข้อมูลแบบจำลองเนี่ยเป็นการตัดสินใจที่เร็วขึ้นเป็นระบบขึ้นประสานกันมากขึ้นนะครับแล้วก็ถือว่าเป็นสิ่งที่น่าจะมาช่วยแก้ปัญหาโจทย์ปัญหาด้านน้ำของไทยได้นะครับโอเคครับก็ต่อไปก็คงเป็นช่วงถามตอบละนะครับก็เปิดโอกาสให้พวกเราถามคำถามก่อนขอไมค์ด้วยครับเชิญครับ
We talk about the platform. What about the security? The API key, authentication, because this system you use is to run the system used to cope with the disaster. So, is the platform come with any type of authentication that used to protect the system itself?
Yeah, very good question, and the short answer is yes. It's fully protected. So So there's different ways to implement the system. So you can do an on-prem installation, so on your own servers, and then you can also arrange basically the security of your own servers here at RID. When we integrate in the cloud, basically everything goes through login, authentication, authorization, using global standards for that. The software itself is scanned on a daily basis for IT security risks. Also there we use basically the global standard scanning tools to scan every day the code where and you know every day new vulnerabilities pop up, so we patch them. We inform our clients to install those patches. So yeah, it is very secure. It runs on the secure environments in the UK, in Australia, in the US, in the Netherlands. So I think it's well protected basically. Yeah.
And you talk about universal. So any telemetering station and other types of the measurement input, do you have any standard that used to input into this system to be processed? Is it CH3 or we have to pre-process the data before input into this swarm system?
Yes, also very good question. So at this moment, I think we can process natively around 150 different data types already. What we typically do is if we have a data provider with a sort of a specific data format, it's for us typically not a lot of work to develop what we call a import adapter, just to make sure that the data provider doesn't need to do any processing, because we know every script or every tool that you put in between the data and the database basically is a point of failure in the workflow. So we tend to make sure that the data can be imported as is, as much as possible. And that is already possible for around 150 different data types, including all standard data types like GRIB data for weather forecast data, well, CSV obviously, XML, but many different data types can already be imported, and usually the one that you need is already there, and otherwise it's a small development to make it happen. Yeah.
So you talk about the new normal. When you build that gate, okay, what return period that you use to design such gate?
Yeah.
100 years? Because nowadays, 100-year return period become only 50 years return period.
Yeah.
So when you build that gate at the Delta, what return period that you use? Because Mr. Nangkwe, he gave me information that if you can protect only one disaster, it's worth to build that gate, right?
Yeah.
Okay.
Yeah. So that is, of course, it's this is I always say it's the $1 million question. What is the actual return period? And I think even without climate change, it's already very difficult to calculate the return period, because we only typically measure for 50 years. If you're lucky, you have 50 years of data. So that means that you can, with some form of confidence, maybe say something about the 10-year, 25-year return periods, but not much more, because that one point at the end of your tail can be an outlier. If you would measure for 10,000 years, that point could have been your 10,000 years. So I think it's a very difficult question, and in a changing climate, it even becomes more complicated. So the only thing I think you can do is to look at a lot of different scenarios, and that's also where models can come in, because they can help, let's say, investigating also sensitivity to some of these choices. But if you really bring it to the economic, let's say, the economics, where typically the return periods really come in. What is your annual expected damage, and with that your rate of return on investment? That remains a very complicated story, and I think there's a lot of uncertainty actually in those estimates. And my take on that is, I think the worst you can do is to ignore those uncertainties and just so I think to do a lot of simulations and show also how things might change if the situation is changing. I think that is that is already a good starting point to show. The other thing that we also now are trying to do more and more is to turn it a bit around, and then we come to this, maybe that one flood is already enough to pay back the investment. You can also do more bottom-up approach where you say, well, we do sort of stress testing the system, and together we decide what is the level that we find acceptable in terms of remaining risk, and what is not acceptable anymore. And in the end, that's sort of a different way and more of a collaborative way of coming to an agreement rather than a very mathematical way of very rigorous focus on the return periods. But yeah, I don't have a very clear answer because I don't think there is a clear answer for this. Yeah.
Appreciate the answer. Thank you.
ครับเชิญครับข้างหลังใครอาจารย์กิติเวชก่อนก็ได้ครับเชิญครับ
Thank you very much, Mr. Mark. I'm Kitiwet from Konkan University. I have actually two questions to ask you. The first one is about, can you tell us about your experience and also your understanding about data sharing, in the Netherlands?
Yeah.
Because in Thailand, we have so many agencies dealing with the data collection, and also, they, gather the information and they keep it. The big problem is that it would be better if you could share the information together and incorporate based on the data that we have. I like to know a bit about the mechanism of sharing the data in the Netherlands. What are they? How can you deal with so many various source of data? How could you share with that? The first one. Thank you.
Yeah. A very, very important, relevant question, and maybe just to I worked a lot in many countries around the world, and Thailand is not alone in that it is difficult to share data between agencies or between data providers. I work now for 4 years in Singapore. In Singapore, also very complicated for sharing data between agencies, etc. And I think in the end, how that works in the Netherlands, in the end it was a government decision that was made at the highest level. Like, well, hey, it's important that we share that data because it will improve our understanding. It will improve basically the capacity also of our industry, because by sharing data and information that was sort of done by one company first, if another company comes in and needs to sort of start from zero, it takes very long to sort of together build up the capacity to a higher level. And I think that is what also the Dutch government realized. Well, if we say, well, it's Dutch government that funds the projects and that funds those data collection effort. For example, LiDAR data collection is funded through the Dutch agencies, like a Dutch government. They say, well, then it should be available for everyone to use that data, because it's one company that does the measurement, but it was paid by the government, so it should be open data. So I think it's at the highest level it was enforced like that. For Deltare specifically, so we are what we call a applied research institute. We are a national research institute, and that comes with additional obligation that everything we do from public money needs to be open. So that is also all the reports, all the models that we develop for the Netherlands, they need to be open so that others can build on top of that. And that's how you gradually build up the capacity and build up the ecosystem in which everyone learns together. And you can also then challenge each other, right? And I think that's also part of it. You can then also point out, well, hey, you made this choice. Why did you make that choice? Based on which information? Yeah, I have this idea, and then slowly you build up that ecosystem, but it is ultimately a decision from the government that triggered this, I think. Yeah.
About my second question, I'm very happy to hear Delphius because I used Delphius 15 years ago for my PhD in Delft.
Oh, wow.
Yeah, but I know a little bit about Delphius. But my question is that in case we need to upgrade the system, right? Do we need to recalibrate the model, especially to adjust the parameters? This kind of thing, I'm sure that based on your consultation, right, to the national agencies like RID. Yeah. So, do you have any suggestion for the regular period that we need to use it for the recalibration of the model?
Yeah, that's a very, very good question. So maybe first of all, so Delphius, you don't need to recalibrate because the platform itself you can upgrade, but the models that you might run, they might need recalibration. But that, of course, it depends a little bit on what changes are you looking at. So typically, if you look at changes in the software code, only rarely, I think, a recalibration is needed. Only if like it's a major change from let's say version A to version B, completely different formulations behind it, etc. But that only happens very rarely, I would say. More frequently is that when you say, hey, we've done a new measurement campaign, we have new cross sections. We want to integrate those in the model, or we have a new digital elevation model, we have new rainfall data sets, so those bigger changes, and especially I think the ones that affect the layout of the system, those will trigger, let's say, a recalibration effort. What we typically advise, and that's also what we do in the Netherlands, so the Deltares manages the national models for the Dutch government. And basically so these models are there, and every 2 or 3 years they do a new bathymetric survey, and that data is then so Deltares is then tasked to say, hey, there's the new data, we make a new model schematization using the new bathymetric data. And what we've done, we've set up a sort of a test bed of simulations with standard simulations, and basically we run that then using the new model schematization, and if the differences compared to the previous version of the model are above a certain threshold, then we say, okay, that the difference is too big, so you need to recalibrate because we don't trust the model. But you can decide on the threshold. I mean, if the difference is in like 1 or 2 millimeters or centimeters, you say, well, it's acceptable, we understand that. But if it's 10 centimeters, or maybe a whole area starts flooding that previously did not start flooding, in the same simulation, then you need to rethink. But I think having that test bed, having like your standard set of events that you simulate with the software, is a good starting point for maybe RID to have for the models that they have, to store the model, including some of those test simulations for any upgrade of the modeling framework.
Yeah, because by that time, since I started, it was like 20 years ago. And I worked with Mika Werner.
Yeah. I was going to ask, yeah.
And by that time, I coupled the SWOT model with the SOBIC. SOBIC 2D. And then it was a bit difficult, because the adapter to adjust the data format. Like you said, you have 150 formats, right?
Yeah.
By that time, I used the XML in collaboration with the MATLAB, to give the order to the software.
Yeah.
So that's why I learned from that. By that time was that like I need to recalibrate just in case the land use has been changed a lot, and also with some physical information, like cross section or something like that.
Yeah.
That's why I like to get some suggestion that how often we have to recalibrate the model.
So how often? I think it depends very much on how quickly the system is changing. Well, we just heard this morning about sediment. So that was sediment in reservoirs, but sediment in the rivers is typically what triggers changes in the geometry of your cross sections. Yeah, depending on your system, that can go either very fast or very slow. If you have a highly dynamic system that changes a lot, I would say you need to measure bathymetry every 2-3 years. That's what we do in the Netherlands, for example. And then, implement it in the model, run your test simulations, and then decide yes or no recalibration. But some systems, they're very, changing really not a lot. So then you can, So it's I would say it depends on the river or the basin that you're working on.
Okay. Thank you.
โอเคครับขอบคุณครับมีคำถามเพิ่มเติมอีกไหมครับอาจจะได้สัก1คำถามมีไหมครับมีไหมเอ่ย หรือว่าเริ่มหิวข้าวกันแล้ว ในเวลาอาหารกลางวันเนาะ
One question there.
โอเคน้องนิสิตได้เลยนะเชิญครับ
Hi. Hello. First, sorry for if my sentence or the grammar is wrong or right.
No problem.
Okay. I just want to know for like student, what type of training or resource do you recommend for students who want to become proficient in using this program?
Yeah. Oh, that's a good question. So I can tell you my story, how I became an expert in this. So first of all, so my background is in civil engineering with a specialty in water management from the TU Delft. And I think what I learned there, which is critical, is programming. And computer programming learned me to understand how computer programs work. I learned MATLAB at the time, a little bit of Python. And by doing that, you develop sort of a base set of skills that you can apply later on in other types of systems and programs as well. So I think if you're still at university, spend time on learning computer programming, because I think it's a very valuable skill to develop. Then the second part of my story was, so after graduation, I went to work at Deltares at the time. And basically the first 3 years of my career, I just spent on developing this kind of systems. So, and that was from very simple tasks, writing, importing like a CSV file into the system, to more and more complex systems. And the key is to, after that 3 years, keep doing it, because you keep learning, you keep improving yourself. Unfortunately, nowadays I do less and less of this kind of work. So I'm more on that right side of that graph, on talking about how to design these systems, but I'm not building them myself anymore. But building them, just spend a lot of time with the system. And one thing that I think is critical, and I think that relates also a little bit to my last key takeaway, the organizational capacity. If you are alone, if you're the only one that knows about it, you cannot learn, or at least it's difficult to learn. And I had the luxury that I was sitting next to 5 other experts in this, that they were all sort of more senior, more expert than I am, so I could also walk to the desk, ask a question. So I think that is, if you really want to develop and learn, then you need to find an environment where you can learn from your peers, your colleagues, and because I think that's important. And that's, I think, what I mean with this organizational capacity. It's like it's a shared effort, and it's not individual persons that will bring the organization to a higher level. It's really like an collaboration along the different disciplines and the different colleagues. I hope that gives you a bit of inspiration. Yeah.
Thank you.
โอเคพอเข้าใจเนาะเขาบอกว่าสำคัญสุดเริ่มต้นเลยโปรแกรมเขียนโปรแกรมมันไม่ได้อยู่ที่ว่าจะต้องใช้ซอฟต์แวร์อะไรนะคะเพราะว่าอย่างอาจารย์เองอันนี้ส่วนตัวเสริมให้เนาะว่าการเรียนบางอย่างบางทีเรายึดติดกับซอฟต์แวร์ใช่ไหมทางอาจารย์เห็นลูกศิษย์หลายคนเหมือนกันยึดติดกับซอฟต์แวร์ว่าใช้ซอฟต์แวร์ตัวนั้นตัวนี้แต่จริงๆไม่ใช่จริงๆเป็นเรื่องของตัวพื้นฐานความรู้เลยนะครับอย่างถ้าตัวเนี้ยน่าจะเป็นลักษณะของโปรแกรมมิ่งหรือตัวอื่นเหมือนกันก็คือเบสิกความรู้ที่เกี่ยวข้องเนาะนะครับเบสิกเราแน่นนะครับไปต่อซอฟต์แวร์ตัวไหนได้หมดเลย
นะครับและที่เหลือก็คือเก็บเกี่ยวประสบการณ์ถามรุ่นพี่ถามคนที่เขาทำเป็นนะครับกล้าถามอันนั้นก็จะทำให้เราได้ประสบการณ์และแข็งแกร่งเพิ่มมากขึ้นนะครับโอเคก็คิดว่าก็คงจะไม่มีคำถามแล้วเนาะเพราะว่าได้เวลาอาหารกลางวันละโอเค thank you Mr. Mark for your time and for sharing your experience with us today โอเคขอเสียงปรบมือให้กับ Mr. Mark ด้วยครับ
และในโอกาสเดียวกันนะคะขอเสียงปรบมือให้กับดร.ชูพานชมพูจันทร์ด้วยค่ะ Mr. Mark please remain on the stage we have the session of the present the souvenirs ตอนนี้โอกาสนี้ขอขอบคุณดร.ชูพานชมพูจันทร์เป็นอย่างสูงเลยนะคะเดี๋ยวให้ตากล้องถ่ายภาพรูปหนึ่งในการเห็นเดินขึ้นไปแล้วนะคะโอเคเดี๋ยวเราอยู่ตรงกลางเวทีสักนิดนึงหยับซ้ายสักนิดนะคะ a little bit left yeah at the middle of the center and we take a photo one shotแล้วก็หลังจากนี้นะคะเดี๋ยวจะเป็นช่วงเวลาที่เราจะมอบของที่ระลึกนะคะให้กับมิสเตอร์มาร์กนั่นเองค่ะดังนั้นเดี๋ยวขออนุญาตขอเรียนเชิญดร.ชูพันธ์นะคะลงไปพักที่ด้านล่างเวทีก่อนนะคะขอบคุณเป็นอย่างสูงเลยค่ะอีกรูปหนึ่งแล้วตากล้องโอเคเรียบร้อย Mr. Mark please remain on the stage and at this time ขออนุญาตเรียนเชิญนะคะคุณรสุสืบสหการค่ะผู้อำนวยการสถาบันพัฒนาการชลประทานเพื่อที่จะขึ้นมามอบเป็นของที่ระลึกนะคะให้กับ Mr. Mark Hagnall นะคะที่วันนี้มาพรีเซนต์กับเราในหัวข้อของ Food Risk Management through Resilient and Sustainable Infrastructure Solution using Dove Fields นั่นเองค่ะวันนี้โอ้โหต้องบอกว่าดร.ชูพานชมพูจันทร์จะยังคงอยู่กับเรานะคะในช่วงบ่ายก็เช่นกันนะคะก็ยังไงก็แล้วแต่เดี๋ยวเราได้อยู่กับท่านยาวๆเลยขอบคุณท่านเป็นอย่างสูงเลยค่ะที่วันนี้ได้มาดำเนินรายการบนเวทีค่ะทำให้เราเข้าใจในเนื้อหาที่ลึกซึ้งมากยิ่งขึ้นแล้วก็เหมือนไขกุญแจของปมความรู้ต่างๆนะคะแกะออกมาให้เราได้เข้าใจไปเป็นประเด็นเลยนะคะดังนั้นวันนี้ต้องขอบพระคุณท่านเป็นอย่างสูงในช่วงเช้าด้วยค่ะแล้วก็ in this time Thank you very much, Mr. Mark Hagnall, for your amazing presentation. That was really an informative session. Thank you very much. แล้วก็ขอบพระคุณคุณรสุสืบสหการด้วยนะคะที่ให้เกียรติขึ้นมามอบของที่ระลึกในช่วงเช้าวันนี้ค่ะน้องๆคะก่อนที่เราจะลงไปพักเบรกอาหารกลางวันกันอย่าลืมนะคะตามที่แจ้งทุกท่านเลยค่ะเดี๋ยวหยิบมือถือขึ้นมาสแกนเช็คเอาท์นะคะลงทะเบียนเช็คเอาท์สำหรับ QR code นี้สำหรับคนที่ต้องการเก็บคะแนนนะคะตัวคะแนนของCPD ค่ะก็เมื่อเช้าที่ได้แจ้งไว้แล้วว่าจะต้อง3องค์ประกอบครบด้วยกันก็คือ QR code ด้านหน้าห้อง QR code ตอนลงทะเบียนเช็คอินตอนเช้าตอนเวลาประมาณเมื่อเช้าประมาณ9 นาฬิกาเนาะ 9:00 แล้วก็อันนี้ต้องเช็คเอาท์ด้วยนะคะไม่อย่างนั้นจะถือว่าเซสชั่นตอนเช้าทำมาไม่มีค่าอะไรเลยนะคะจะไม่ได้คะแนนแบบถูกต้องตามกระบวนการดังนั้นอย่าลืมนะคะเช็คอินแล้วเช็คเอาท์ด้วยอันนี้พี่เตือนให้ตลอดเลยนะคะก็หยิบมือถือขึ้นมาเช็คเอาท์ตาม QR code นี้ก็เป็นอันเสร็จสิ้นได้รับคะแนนสำหรับเซสชั่นเช้าในวันนี้ค่ะส่วนในช่วงบ่ายค่ะเราก็จะยังมีช่วงเวลาของการกลับมาเก็บคะแนน CPD กันอีกครั้งหนึ่งกับหัวข้อในช่วงบ่ายนะคะซึ่งก็จะมี QR code ให้น้องๆได้เช็คอินอีกครั้งหนึ่งนะคะในช่วงบ่ายนี้เราจะมีหัวข้อมากมายเลยทั้ง3ประเด็นซึ่งเดี๋ยวจะมาสรุปให้น้องๆฟังกันอีกครั้งหนึ่งก่อนที่จะเข้าเซสชั่นนะคะแล้วก็ท้ายสุดของวันนี้ค่ะเราจะมีการสรุปประเด็นโดยผู้ช่วยศาสตราจารย์ดร.ชูพันธ์ชมพูจันทร์อีกครั้งด้วยค่ะยังไงก็วันนี้ก่อนที่จะไปรับประทานข้าวรบกวนขอให้ทุกท่านปรบมือดังๆให้ต้องเรียกว่าเป็นผู้ที่ขึ้นมา present บนเวทีนะคะ speakers ของเราแล้วก็ moderator ของเราดร.ชูพันธ์ชมพูจันทร์อีกครั้งหนึ่งได้ไหมคะเอาละค่ะ so I just asked them to give a big round of applause for you to present on the stage. That was really amazing. เอาละค่ะทุกท่านคะเดี๋ยวให้ทุกท่านไปพักทานข้าวกลางวันกันก่อนแล้วเดี๋ยวเรากลับมาเจอกันที่บนห้องนี้เวลาเดิมนะคะ 13 นาฬิกานั่นเองค่ะโดยประมาณเราจะเริ่มเซสชั่นที่น่าสนใจในช่วงบ่ายค่ะแล้วเจอกัน 13 นาฬิกาสวัสดีค่ะ